keep engaged with the material, right? That didn't really work so well, so this time I'm going to be mostly off of slides, all right? And that means that this is a very difficult task, right? I have to keep you guys engaged, seeing math, right? Because anything quantum is mathematical, right? There's no getting away from it. For 3 hours, and you're not going to be taking notes or anything, and that is a very difficult task. So guys, you're going to have to pay lots of attention. In order to stop you guys from getting too bored and losing the thread of what I'm talking about, I'm going to talk fast. We're going to do it like if you ask any of the kids, any of your kids or anybody's at university today, when you learn off of YouTube, what do? You put the lecture in 1.5 times or 1.25 times, and then when you miss a bit, you rewind back, okay? So that is what we are going to do here, all right? I'm going to try and talk fast as much as I can. That's hard for me, but I'm going to attempt to, all right? And when you miss a bit, all right, you guys are going to shout out and say, what the hell did you just say, right? Okay? So that's the idea. All right, it's going to work better. I know you guys were kind of going to sleep up the back there. Steph has given me this great big room, which I was expecting to get a little room. It's going to be better if guys who are, further back move up so that I can see your faces and judge, are these, faces blank or not? So really it'd be better. And so that, we can interact a little bit more. This will work better if we can interact. All right. So look. Yes. Yeah, shout at me. Yeah, you are not going to put me off my, rhythm. All right. You absolutely interrupt me. That's the point. Okay. Right. Yes. Yeah. Sure. So, everybody nice and close up. I'm going to talk fast. Stop me. Shout out at me when something's unclear. All right? Okay. So, I think I'm just about at start time. So let's get started. We're going to talk about quantum information. Oh, God. That's a bad start. Oh, wait, I know it. There we go. Okay, so why? Basically, this is the easiest way to learn, one of the reasons is this is the easiest way to learn quantum mechanics. All right, quantum mechanics is a famously kind of difficult topic, all right? But it's not that difficult, but it's difficult. And one of the reasons for that is that when you learn quantum mechanics in the context of particle physics, there's a whole lot of integrals. Now, we can skip all that complexity if we talk about quantum information, where we're working in finite dimensions. And instead of integrals and functional analysis, we're talking about vectors and matrices like what you learned at high school. So quantum information has direct applications in quantum computing and in quantum communications, which is technology which is not quite here yet, but believe me, the company I now work for the past 5 days or something, IBM, is investing huge amounts of money in developing real devices which can really perform quantum computations. We're now in the regime of hundreds, thousands of qubits. They're kind of shitty qubits. They're not very good qubits so far, right? But they're getting better all the time. And when we get to a particular scale and we'll be able to do noise correction, then we'll really be able to do actual computations. This is also, quantum information is also the best way to understand entanglement and the theory of open quantum systems, which is quantum systems which are coupled to the environment, and that includes every single quantum computer. Every single quantum computer is there in a fridge, but the fridge is not perfectly insulated from the environment. There are magnetic interference, and finally, quantum information is, to me, I'm not an expert in quantum foundations, but it is the best way to get an idea of, to start to think about, these famous problems like the measurement problem, like what happens if we poison a cat based on the radioactive decay of some element, and these quantum foundation problems of understanding what quantum mechanics means, right? From that, I think the quantum information perspective is absolutely essential. What I am above anything else going to try to answer in this question is why quantum computing is so hard, and I'm not talking about from the hardware side of things. From the hardware side of things, quantum computing is definitely hard, right? H bar is 10 to the minus 34, okay? Anything at the quantum scale is so astronomically far from the scale of everyday things, right? That it is amazing that we can build qubits, right? But we can. All right? And that is a problem which people are working on and which, in my opinion, looks like it's getting solved. Where we're still, in my opinion, as far as I can tell from everything I've read, like really kind of stuck is once we have these qubits, once we have these quantum computers, what are we going to use them for? The only, thing we sort of, application such as it is that we really have is factoring really large numbers, and that has only one application, which is, breaking the RSA security protocol. And by the time, hopefully nobody's using RSA by the time real quantum computers arrive, right? So the question is that we need to develop algorithms that can actually run on these quantum computers and that are going to be better, that are going to provide some advantage over classical computing. All right, so our plan here is we are going to start off the first hour. We're hardly going to talk about quantum at all. We're going to talk about classical information and about probabilities in a really weird notation that's going to turn everybody off, okay? The biggest problem with understanding the mathematics of quantum is that the notation is super weird, okay? But it's good. It's actually, it's weird, but it's beautiful and elegant, and I personally love it, okay? So if you get nothing else out of this, I want you to get a little bit familiar with the notation so that afterwards you guys can go to the Qiskit website or whatever and start making sense of quantum information, quantum computing by looking at it. But as soon as you go to Qiskit, you are going to be hit by bras and cats right in the face, okay? There's no getting around it. This is the notation which is used universally in quantum. The second hour, we're going to start to talk about, quantum mechanics in this finite dimensional setting. And the third hour, if we really manage to make it that far, we're going to talk about quantum circuits, about entanglement, I'm hoping to hell we can arrive at the no-cloning theorem, which is this weird thing that gives some real insight. So the first hour, we're starting as of now at 2:05. So we're going to start off considering an experiment in classical, a classical probabilistic process. We have an experiment X. It has a discrete, finite, labeled set of outcomes that belong to this finite set. Okay, this X would be called a random variable in classical probability theory. Examples of this are tossing a coin. The outcomes are heads and tails. Rolling a dice. Arriving at a traffic signal. The outcomes are, red, yellow, green. A classical probability distribution assigns a number to each element of the set of outcomes. Okay, so normally, traditionally in classical probability theory, we consider that a function, right? A probability distribution is a function. And here, we're actually going to represent it as a vector. So, for example, our fair coin system, our fair coin experiment, is going to be a vector of a half and a half, and our traffic light experiment is going to be a vector with 3 elements. The probabilities of getting red, yellow, and green. We can write any such distribution as a vector, but is any vector a distribution? I mean, are those good distributions? I mean, no, they're not, right? The reason is that each probability has to be a non-negative real number, and the probabilities have to sum to 1. Okay, so in classical probability theory, these are the restrictions on what makes a vector a legit probability distribution. Now we're going to do something funny, which is going to look like completely useless. Why am I even doing this? I'm going to distinguish between 2 types of vectors, right? First of all, we can have a vector which can be written as a matrix with 1 column. Right? I could do that. Or as a matrix with 1 row, I'm going to call this a dual vector or a row vector. Obviously, these are the same thing. There's a completely trivial isomorphism between the space of column vectors and the space of row vectors, all right? But it's going to be useful. And we label these column vectors using this funny notation, which you've probably seen before, because if you ever search for the word quantum, this is the thing which comes up, okay? This thing is called a ket, this thing. And it's a ket. It has a pointy end to the going that way. On the other hand, a row vector is called a bra. It has the pointy end going that way. And there's nothing fancy here, guys. This is just a funny way of labeling variables in high school maths. What's nice is the label can be anything we like, all right? So it doesn't have to be a psi. It can have NLM. That's an angular momentum eigenstate. It can be plus. It can be spin up. It can be some binary digits, right? So whatever is enclosed between the bar and the pointy bit, that's the label. That's a label which tells you what what ket we're dealing with here, what column vector we're dealing with. Oh, yeah. There's an operation which everybody's learned in high school called transposition of a matrix, okay? Transposition maps row vectors to column vectors or vice versa. So we have a you know, this is the isomorphism I described between the two views. And so for vectors of real numbers, right? For real numbers, the relationship between bras and kets is just transposition. Nothing more exciting than this. We're going to have to change this for quantum. It's not going to be so simple. You also in high school learned about the dot product. Okay? The dot product between two vectors is like an element-wise multiplication, sum it together. Take this. No, don't take the square root. We can write that in terms of our rows and column vectors. If we consider that, you know, if we have two kets and we're taking the dot product, the inner product of them, then we consider that as taking the transpose of the first one, so flipping it side, and doing matrix multiplication between this row and this column, right? And that gives you the inner product. Now we're going to start changing our notation. We've already said what was the relationship between bras and kets, so we take the transpose and we can write it that way. And then, as an abbreviation, we write it like this. Okay, this is always a number, and we're never going to use dot products ever again. We're always going to write inner products in this form, and you always know when you see that, when you see an equation with something that looks like that in it, you know it's a number, which is extremely useful. In the jargon, we call that the overlap. That's usually because they're usually normalized. The length of a vector is the square root of that. It's the same definition from high school. The length of a vector is the inner product of the vector with itself. Take the square root. Okay? Yeah, as in square root of a squared plus b squared plus blah, blah, blah. So what's the length of this vector? Somebody tell me quickly. Square root of 2, exactly. So any time in these slides where you see 1 over square root 2, 1 over square root 2s are not telling you anything interesting. They're telling you that we had a normalization factor that turned our vector into a vector of unit length. Okay, so that's where all the 1 over square root 2s come from. Okay, every time you see it on the slide. Vectors are perpendicular orthogonal if the inner product is 0. Right? Again, high school maths. Are those two vectors orthogonal? Yes. So we have 1 times 2 plus 1 times minus 2 is 0. So now we can talk about, you know, this is the fundamental, most interesting and important thing in linear algebra is the notion of an orthonormal basis, okay? An orthonormal basis is a set of vectors. In our case, because we're working with finite dimensional Hilbert spaces, this is always going to be a finite set of vectors, where each vector has unit length, so length 1, so its inner product with itself is 1. The vectors in this set are mutually orthogonal, so each one of them, they're a perpendicular set, and the size of the set we can call the dimension of the vector space, okay, which, as I said, in our case is always going to be finite, a finite number. For example, for our heads, tails probabilities, stochastic experiment, whatever you want to call it, we have two basis vectors, which are the ket head and the ket tails, and they look like that. Let's check. Is this basis orthonormal? Well, let's check heads with itself. What's heads times heads? 1 times 1 plus 0 times 0. That's 1, so that looks good for a vector that should be of length 1. And now we multiply them by each other. We get 1 times 0 plus 0 times 1. That's 0, so they're orthogonal. Okay. So we check that is an orthonormal basis. Now the thing that makes basis so important is that any vector in this space can be expanded in terms of the vectors of the orthonormal basis. Okay. Now, is anybody seeing this for the first time? Okay, a significant number of people. Okay, right. So this comes back to what do we mean when we talk about the dimension of a space? Okay, the dimension of this space, this vector space we're in, is 3 because there are 3 directions we can move in. Okay, I can express any point within this space in terms of something times this direction, something times this direction, and something times this direction. Okay, that's all it is. Okay, so here, this is a 2-dimensional vector space. There's only 2 possible outcomes to flipping a coin, so the basis vectors are heads and tails. And if we have a fair coin before we flip it or before we look at the result, the probability distribution can be expressed as this sum, which is this vector here, can be expressed as this sum of the 2 basis vectors heads and tails, the 2 basis kets. I know this is a really funny notation for describing a probability distribution, but it's not telling you anything which you didn't already know. Probably this is a half, probably this other thing is a half, okay? It's just a weird notation. We can also expand it, any vector as in bras as well. It's just exactly the same thing. Okay, in general, we have the formula that any vector is a sum of some set of numbers psi I times basis vectors, which we can label by I, by natural numbers, okay? 1, 2, 3, 4, okay? And we also get a compact definition of what it means for a basis to be orthonormal, right? We say that the inner product between the basis vector I and the basis vector j is delta ij, which is this funny symbol beloved to physicists, which just means 1 when I equals j and 0 when I equals not equal to j. So that expresses in one compact form the idea that the basis vector with itself is 1, the basis vector with any other basis vector is 0. Okay? And this is a very, very useful thing to use during calculations. Now, we can now express the probability of any given outcome for our experiment as an inner product between the basis vector, in this case heads, and the probability distribution, or the state vector, I might sometimes call it, which is psi, okay? Some arbitrary vector in this vector space. In our case, we're talking about half-half, okay? So let's see what happens. Let's check this. For this state, what we said was our distribution of a fair coin. So what happens? We're gonna multiply this by the heads bra from the left. It's going to come in, go straight through the number. Okay, vectors don't care about numbers. Go straight through the number. It hits h. Now we have h. H with itself is 1. It also gets distributed over here, so it also comes in and hits tails. ht, heads tails, is 0, right? So what we have is we have half times 1 plus half times a 0, and we get the probability is a half. It's correct. That's what we knew the right answer had to be, okay? Nothing, I'm not doing anything fancy here, guys. This is just like, a funny way of writing things. So, in general, we can write the probability of any given outcome using an inner product. I'm not going to prove it. I don't have paper here. Blackboard, I mean. We're going to, again, modify this for quantum. We can even, nobody does this, all right? This is just something I'm saying, but we could even talk about computing the, when you're doing, in classical probability theory, one of the main things you want to do is compute the average value of a random variable, right? The expectation or the mean, right? And so we can even think about what in our new funny notation would be the way to compute an expectation. Well, really, we can do it as an inner product. So let's see what we say. Okay, so say I'm playing a game where heads wins $1 and tails loses $2, euros, whatever. And so the average, my average winnings is going to be the inner product of shit. Oh God, sorry. Is going to be the inner product of this bra here, this row vector here, with the winnings, with the probabilities of the outcomes, which is the state vector, the probability distribution here of half and half, and we get some number out, okay? Nobody does this. I'm just showing you what, if we were in classical probability, what would be the notion of an observable? Okay, what would be the result? How would you find the expected value, the average value of an observable? And we get something pretty trivial. Why am I telling you this? Because it's going to be entirely different in quantum. All right. Has anybody got any questions at this point? If that wasn't clear and kind of stupid, because what did we really do? We just learned a funny notation. Let me know. Okay, Steph? Yeah. No. So, actually tossing the coin and observing the outcome has the effect of collapsing a probability distribution. So, before we toss the coin, we could say that the state of our system was this ket we were just talking about, of a half and a half, right? Half heads plus half tails. And we could call it a superposition of the two states. After observing heads, our knowledge of the state is now represented by just the ket H. So, what we've observed is this famous property of classical systems in physics called superposition and wave function collapse. Now I'm being kind of silly here, right? Because those are things that people associate in their heads with quantum mechanics. But in fact, in my opinion, that is false. They are properties of a stochastic system. They are not properties of quantum. Quantum systems have superpositions and wave function collapse because quantum is a stochastic or probabilistic description of nature. But there's nothing in there which is, from an information processing perspective, specific to quantum. So whatever it is that quantum computers are going to do for us that classical computers can't, it is not going to come from superposition or from wave function collapse. Okay, we're going to see later where it has to come from. It comes from something far more subtle than that. All right. So people who say, "Oh yeah, quantum computers can do a computation with infinity number of numbers all at the same time," we're going to see that it's way more complicated than that. Let's talk about entropy quickly. I'll try to get through this fast. Probably going to fail because it's probably going to be a little bit interesting. So the entropy of a probability distribution is a measure of how much information you gain on average by performing some experiment. How can we quantify this? Well, let's think about it. First of all, for a basis state like heads or tails, the entropy should be 0. If I know if I know that there's only one possible, if I know the probability distribution says heads has probability 1.0, and I look at this and I open it up, I look at the result and I get heads. Have I gained any information? No, nothing. Right? It should be non-zero for any state that's a superposition of more than one of the basis states. It should be additive. Okay, and this is subtle and important. So if I flip 2 coins and observe their responses, I get twice the amount of information. Now think about it. Probabilities are not additive. Probabilities of independent events are multiplicative. The probability of getting heads and heads is a quarter. It's half times a half. So we're going to have to come up with something which turns something that is fundamentally naturally multiplicative into something that is additive. Does anybody know a function which does that? Yes. Yes. Are they independent? Same thing. Yeah. It doesn't matter whether they're at the same time or one after the other, whatever. Okay. Or if we flip it once and then we flip it twice. Yeah. It's all the same, right? We still get twice the amount of information, right? Yeah. because we're modeling them as independent. If they're not independent and one is the result of one coin flip, one coin toss is affecting the result of the other coin toss, okay, then things are more complicated. There's way, the entropy will still be able to capture that, but it's we'll come to composite systems in a second. Okay, we actually come to composite systems later. Just consider that they're independent coin tosses, right? And all I'm saying is that as long as they're independent, probabilities are multiplicative. The probability of getting heads and heads together is a half times a half is a quarter. But we are looking to come up with a formula where the entropy of this coin and the entropy of this coin add together so that we get twice as much information from flipping two coins, not 4 times as much. Yeah? Does that make sense? Okay. Everybody else? Okay. So we can talk about the self-information of a single event, of a single outcome. There's a quantity which people don't talk about much, but it exists, and even I actually found the name of this quantity in a book about machine learning, about neural networks, the Goodfellow book. So the self-information of an event is the negative log of the probability. Why the negative log? It sounds a bit strange. Well, to make it plausible, to start out with, what is it for if psi is 1 for a certain event, for a certain outcome? Log of 1 is 0. So we get 0 information out of a certain outcome. Well, that's good. That's what we're looking for. What is it in the limit where psi gets really small when psi is 0? Negative infinity. So that tells me I get, it's minus infinity times minus is positive infinity. So I get an infinite amount of information out of observing an impossible event, which is also correct. Right? If I observe an extremely low probability event that I judge according to my prior, then observing that gives me a lot of information about the world. Okay? More importantly, that's what I just said. By the way, everyone here is computers. What are the units of that quantity? Bits, yes. Units of information or entropy are bits. Okay. So now, why is log so magic? Because log is the function that turns multiplication into addition. Okay. That is what's so magical about log. That's why people used to use these slide rulers and stuff, is they could do complicated multiplication just by adding numbers together. So taking the log of things turns multiplication into addition. So a quantity which satisfies our requirements is the following, right? It's an average over all the possible outcomes. Okay, this is... Okay. So this sum of a probability... Remember, we're using psi-i's instead of pi's, but it's the same thing. They're probabilities. The sum of a probability times the self-information of the event is going to give us the average information that we gain over all the possible outcomes of the experiment. Does that make sense? Shout at me if it doesn't. Okay. We're using a base 2 logarithm here. When we're, generally anything where we're computing oriented, we'll use a base 2 logarithm. That is a non-universal convention. If you're doing statistical mechanics or something like that, people use the natural log, and the units of entropy are nats, not bits. So let's check it out. So let's try it out by just calculating what's the entropy of our single coin toss experiment, right? Okay, I can't do it on the board. But let's see, it should be straightforward, okay? What's the probability? We have 2 outcomes, right? Heads or tails. What's the probability of each of them? A half. Okay, so we have a half times, what's the log of a half? -1, right? Yeah. -1. So we have, and then we have a minus sign out here, so that cancels the negative, and so we have a half plus a half times 1 plus a half times 1 is 1, which is correct. I toss a finger, that's a single bit of information I get out of tossing a coin, right? What about tossing 2 coins? In this case, there are 4 possible outcomes: heads, heads, tails, tails, heads, tails, tails, heads. Each of them has probability of 1/4. So we have 1/4 times, what's the log 2 of 1/4? -2. So I have -2, the negatives cancel, we have 2 times 1/4, and we have 4 of them, we get 2, which is again correct. Okay, toss 2 coins, I should get 2 bits of information. So this formula makes sense. I've never seen anyone properly explain the formula for entropy, ever, in any book, ever. Entropy is something you can interpret as the average surprise. How surprised am I on average by the outcome of this experiment? So it's, you know, it's an expectation over something which measures how surprising each outcome is. I want to finish with this section with just an observation, just to you know, say again, this isn't so different between classical and quantum. Different observers have different knowledge about the outcome of an experiment. You might have peaked, and I didn't, right? So different observers are not required to agree on probability distributions. They're not required to agree on their measures of entropy for even given a single system. Okay, any questions about that section on entropy? Everybody understood it. I don't believe you. Huh? Okay. All right. So as the last part of this, last? 3? Oh no, maybe not. We're going to talk about processes, right? What's a process? We have some classical system, and it undergoes some evolution. You know, I tossed a coin, right? And we end up at a final state. Oh, God damn it. A deterministic process, we're going to call P, is one which takes any given initial state I and results in a known final state F. So if you know the initial state, you know the final state. That is, it's a map, a function with elements of form initial state to final state for every possible initial basis state. So consider the flip operation on a coin. Flipping is not tossing, it's flipping is just turning the coin over. Okay, so it's not stochastic. Heads goes to tails, tails goes to heads. Okay, that's a deterministic process. We can write this as a matrix. This matrix is one of my favorite, one of the most famous matrices in physics. We're going to see it later, a lot of it. So 0, 1, 1, 0. So why does that represent the flip operation? Okay, no, I don't have a slide. So let's apply flip to heads. Who remembers how to multiply matrices? Some people are doing it, so that's good. Right. So good. So if we have the vector 1, 0 here, then we come in 0, 1, 1, 0 is going to be 0. And we can come in 1, 0, 1, 0 is going to be 1. So we get 0, 1, which is our tails vector. Likewise, if we did it to tails, we would get heads back. You can convince yourself with that. Sorry, I don't have a blackboard here to do it. But anyway, if you stare at that enough, you should be able to convince yourself that that is a matrix representation of a deterministic process of turning the coin over. Now we're going to, sorry guys, I apologize, but we're going to have to do this, all right? We're going to write matrices in a funny way, just like we wrote vectors in a funny way. And the starting point of this is to understand an outer product. Does anybody know what the word outer product means for vectors? Yes, exactly. Yeah, it's a product which gives you a matrix from 2 vectors, right? So whereas we wrote inner products as a row times a column, if we do the opposite thing and do a column times a row, then we get that times that, that times that, that times that, and we get a matrix out of it. Okay, so that's the outer product of two vectors, And obviously we're going to write it like that. That makes sense, right? We're writing, this ket here is a column, and this bra here is a row. So a column times a row is an outer product, right? So nothing. We're not learning anything new here. This is just something which you'll often see written. And whoops, I went backwards instead of forwards. So now we're going to see that this actually makes it easy to do these kind of calculations. What's the action of this outer product on the ket H? Well, just look at it. Just write it. Just visualize it in your head. We have ket H, bra T times ket H. That gives me, so it's coming from this side. This is the outer product is coming from this side. That gives me TH here, which is an inner product of different basis vectors, which is 0. Now, what if we do it on tails? We get an inner product of tails with itself, which is 1. And so the outcome is ket H. Now we can write our flip matrix as the sum of two of these guys. Okay? So we know, so consider it. Matrices are these are linear operations. If we know what they do on a basis vector, then we know everything about them. Okay? It's enough. If we can verify that this does the right thing to the basis vectors, we know it does the right thing. Okay? By linearity. Okay? So here, if I put in a heads, right? This term survives. This term vanishes, and we know what the result is. It's tails. If I put in a tails on this side, this term survives, this term vanishes, and I'm left with heads. So we can see that this is a representation of that matrix 0, 1, 0, 1, 0 that does the right thing. So these objects, ij, where I and j are always basis vectors, are a basis for the space of matrices, because matrices also form a vector space. Okay? Well, form lots of vector spaces. Excuse me. So these objects are a basis for matrices, which means that we can always write a matrix in terms of these basis outer products. For example, we can write the identity matrix as a formula you use all the time whenever you're doing any quantum, as the sum from over each dimension of the basis ket with the outer product of the basis ket with itself. Okay, because the identity matrix is diagonal that way. Okay, we're not going to use this formula, so I'm going to go quickly over it. Now, our flip operation is itself deterministic, but we can apply it to a probabilistic state. So for example, if we have psi equals a half heads plus a half tails, if we apply the flip operation to that, what are we going to get? I mean, I think it's obvious what we're going to get. F on H gives me tails, F on tails gives me H, and so I'm going to get back half tails plus half H, I get back exactly the same probability distribution. Okay? So if I had no information about whether this coin was heads or tails, and I turn it over with my eyes closed, I still don't know whether it's heads or tails. I get back the same distribution. Okay? So that works. A stochastic process is one where given a known initial state, we have a probability distribution for the final state. Obviously, I care a lot about this kind of things in quantum mechanics because process in quantum mechanics is not needed to be deterministic. Okay. Right. So let's consider the toss operation. We've done the flip operation, turning the coin over. Now let's consider tossing a coin. We know that this introduces, this takes a known initial state of the coin. Oh, it was heads, right? Now I'm going to take it up, and while it's in the air, I don't know whether it's heads or tails. So I've destroyed information. Is that correct? Yeah. I've created a superposition of states. I've created a probability distribution. Okay. So this probability distribution takes heads to tails with probability of half, tails to heads with probability of half, heads to heads with probability of half, and tails to tails with probability of half. So we can write that as a stochastic matrix. Okay. So each of these elements is, one is, this element here is heads to heads. This element here is tails to tails. This element here is heads to tails. This element here is tails to heads. And each of them has a probability of a half. In bracket notation, it looks like this. Again, this is actually more transparent like this. This is why we like this notation, okay? If you look at this says, this takes a heads to a heads, this takes a tails to a tails, this takes a tails to a heads, and this takes a heads to a tails, all with each of them with probability of a half. A stochastic matrix applied to a vector of probabilities must produce another vector of probabilities. And what that means is it can't just be any matrix. Okay, I can't take the matrix 2, 2, 3, 4 and call that a stochastic process, because that won't produce a vector of probabilities. Because we said that. What defines a vector of probabilities? Non-negative, sum to 1. So the matrices which represent processes are a subset of the set of the possible matrices. In fact, the condition is, which you can go home and try it out and figure out why this is correct, the condition is that each column of the matrix representing the stochastic process must itself be a vector of probabilities. And the reason for that is multiplication of a matrix times a vector is taking a linear combination of its columns. If that didn't make sense, doesn't matter, okay? But that's what matrix multiplication does. There is going to be a very different but analogous condition for quantum mechanics, and that condition is incredibly important and incredibly fundamental. Okay, yeah, now this is the last section of this section, okay? How are we doing for time? 2:40, okay, perfect. I have 20 minutes, this is where we're going perfect for time. So if you have questions, please shout them at me. All right. This is the first section which is going to get a bit hairy, okay? So composite systems. It's going to look scary. What if I flip 2 coins? Now the possible outcomes are heads, 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 tails, tails, heads, tails, tails. So we could say, well, I can represent this easily. I know how to do this from high school. These are the basis, and I know what the probability of each of these outcomes is. So I can write a vector or a quarter, a quarter, quarter, quarter. All right. But, as she said, each of these is also a composite state of one experiment on one coin and another experiment on another coin. And now it's okay if you hate me, because I'm going to introduce this scary-looking multiplication symbol in a circle. All right? Now, you've probably never seen before. How many people have seen the tensor product before, the Kronecker product before? Oh, okay. Nice. Very nice. So this is the Kronecker product of 2 vectors. And it's a weird kind of multiplication. At this point, that's all we really need to know about, is that it acts pretty much like multiplication. All right, so what is multiplication? In terms of major, what are the properties of multiplication? Associativity, okay? A times B times C is A times B times C. Commutativity, no, matrix multiplication is not commutative, so that's not a fundamental thing. Actually, the tensor product depends on how you do it. Some people, if they always label the subsystems, you can kind of treat it as commutative, but it's not really commutative. Distributivity, okay, the really important one, okay? So, we want A times B plus C to be equal to A times B plus B times C, and tensor product satisfies that. Identity for the identity for a tensor product is actually just a matrix, the number, just a matrix with one number, with the number 1 in it. So it works like multiplication. When you're doing algebra on it, you just you pretty much think that you pretty much just treat it like multiplication. All right. So what is it? Well, let's write down what we know about it. The heads tails vector ket is the heads ket tensored with the tails ket. So a 1, 0 tensored with 0, 1. And we get a vector in a 4-dimensional space out of that, right? This guy here is a vector in a 4-dimensional space, so that's there. And the and we can, just to make it more concrete, we can see that each of these elements, represents one of the basis kets from the larger space, right? I'm going to tell you exactly how to determine this stuff in a sec, but for now, I just want you to look at that, see that, okay, these things are elements of a two-dimensional vector space, this guy is an element of a four-dimensional vector space, and the tensor product, the Kronecker product, gives you a way of getting from one to the other. So now let's just do some silly computations, right? Let's calculate psi tensor phi, where psi is that, and phi is that. Oh god, I don't think I wrote it down. Oh yeah, I did. Okay, perfect. Okay, so I've got two. I'm just as an example. Okay, I got two kets here. All right, they're legit kets. Nothing, they're both normalized. So let's find out what the tensor product is. So I told you that it obeys the distributive rule. So I can distribute from there to there, and I get that, a half of heads plus tails tensored with tails is heads tensored with tails plus tails tensored with tails, and then we get that, right? And this makes sense, right? We had a probability distribution of, a fair probability distribution between heads and tails on that side on that subsystem, and I knew what was going on in that subsystem, so it makes perfect sense that I get, half heads tails plus tails tails, right? It does what I expect it to do, right? Agreed? Look wrong to anyone? Right. So let's write this out. Now here's how you actually do this calculation if you have actual matrices with numbers in them, okay? You squeeze this guy into this element here and squeeze it into this element here, and then we've got 1 times 0, 1. Yeah, okay, that's correct. 1 times 0, 1, and that gives you 0, 1, 0, 1. Right? That's how you do the tensor product of vectors. Are you guys reading that correct? Can you see how that works? Okay. Similarly, we can do something where both are probabilistic. We're not going to do it. We're going to go fast. Very often in quantum information, not in normal quantum mechanics, but very often in quantum information, we label subsystems. Okay, so we say I have coin A and coin B. And so the tensor product, and we write in that A and B as labels on the ket, so that we don't get confused, we don't get mixed up which side of the system, which subsystem something represents. Now, okay, here's where we start to get into interesting stuff. Not every state of a combined state, when I'm saying state, I mean probability distribution, since we're doing classical, right? Not every probability distribution on the combined system is a product of two independent probability distributions. This is critical that everybody understands this point. We call these subsystems independent if their combined state can be factorized, okay? So if I can factorize a probability distribution into a tensor product of two probability distributions, these systems are independent, okay? This is just the rule you learned in high school, okay? That the probability of, heads and tails together is the probability of heads times the probability of for two coins, times the probability of tails for the second one, yeah? That, probabilities of independent events multiplicative, okay? Represented in our weird, more algebraic, more higher level way of thinking about the world, okay? We've gone up a meta level, and now we're talking about probability distribution, and we're saying that the probability distributions of independent events multiply together via the Kronecker product. Is what I just said absolute nonsense that make no sense? Yes. Okay. Yes, it was nonsense, right? Yeah, I think it was. So, all right. Let's go back. What do we do when we find an equation we don't understand? What is this thing? It's a probability distribution on system A. Yes? What's this thing? a probability distribution on system B, okay? If they're both fair coins, they're both half heads plus half tails. What's this thing? It's a probability distribution on the combined system of both coins, right? The tensor product expresses a relationship between the probability distribution on the combined system in terms of the probability distributions on the subsystems, right? This is correct for systems which are independent, as in they're not interacting, they're not correlated, right? They're independent in the sense of high school maths, okay? The sense of high school maths is this, right? This is what independent events means in probability theory, okay? The probabilities multiply together. If otherwise they're not independent, that formula isn't correct. But those are not the only kind of states we can write down on the combined system in this four-dimensional vector space. Okay? They don't have to. I can make other states which are not a tensor product of two independent probability distributions. I can come with a probability distribution where there are correlations between things. I was trying not to say the word correlation yet because I steal my own thunder from a couple of slides, but looking at people's blank stares, let me touch base with something you understand. Things can be correlated, right? How do we represent that? Well, one way we can create that is what's called a convex sum of product states. Okay, what is a convex sum? It's just a pretentious way to say a weighted average. Okay, so we can create a probability distribution which is not a tensor product by taking two tensor product distributions and saying I have 20% of this one and 80% of this one. Okay? And that cannot necessarily in general be factorized. Might be able to be factorized in a particular case, but anyway, let's not get too sidetracked on that. Let's just look at an example, a concrete example. Okay, this is a perfectly correlated state. I know it looks scary. Don't worry, it's not. It's easy. This says, if system A comes up heads, so does system B. Okay? That's that distribution. This distribution on this side, which has probability of half, but this thing on this side is saying that A is heads and B is heads. And we're saying that is a probability of a half event, that A is heads and B is heads. Over here, on this side, we're saying if A comes up tails, then B comes up tails. And that is also an event that happens with probability of a half. Right? So this is clearly not independent. And it's also clearly not a tensor product. How are you going to factorize that? You can't factorize that into, something times something else. Try it, okay? If you don't believe me, the best way is to just try to do it, and you can't. So another thing to observe about this particular perfectly correlated state is that after observing A, we now know everything about subsystem B. If we observe that A comes up tails, we know everything about we know that B came up tails, or vice versa, okay? So the entropy of the whole system is the same as the entropy of either subsystem in isolation. Contrast a product state, if we observe A, if we flip two coins and we observe that the first one came up heads, toss two coins, I keep messing that up. If we toss two coins, the first one came up heads, do I know anything about the second one? No, nothing at all, right? And that means that the entropy of the whole system is the sum of the entropies of the individual systems in isolation. So it's the difference between correlation. Okay, in terms of entropy. So now let's go on, and I promise that this is the last section in this section of the course, and I know it's getting abstract, but we're going to plow on, and it's only a few more slides, okay? Suppose we have a process, deterministic or stochastic, operating on system A, and another process acting on system B, independently, okay? These are matrices, right? That we can talk about the process, the whole process acting on the whole combined system as a tensor product of matrices. Again, we often label this the matrices by the system they're acting on, A and B. And so what's the difference now? We have two kinds of matrix multiplication. What is the difference between these two expressions? You guys tell me. What does the first one mean? Yes, but what does it mean in terms of processes, like physical processes acting on a state? Yes, exactly. Perfect. So, oh, whoops. Okay. I should have done 2 more slides. What does the second one mean? What is a state row? A state on the combined system. Okay. So yes, they are acting concurrently, in parallel, absolutely concurrently. That's a good word. I hadn't thought of it saying it that way. I forget who said it, but that was correct. On the combined system. Whereas over here, I just have, well, let me go to the slide. I have Y acting first on a single system, and then X. Note, like this is a pain in the ass, and I mess it up all the time. Okay, this one acts first, and then this one acts. Okay, it's like backwards from what you expect. Over here, we have X and Y acting in parallel, concurrently, on the combined system. Right? So that's what the difference between these two things. Okay, it actually turns out to be super easy to write. A tensor product of matrices acting on a tensor product of vectors. It's super easy. This one just acts on this one just acts on this one, and you get a tensor product back out. And that makes sense, right? If you act on one subsystem with one matrix and you act on the other subsystem with the other matrix, you get something which is that, right? I want to show you quickly, we're not going to get hung up on this, how you write this as a matrix. So we know what our, we're coming back to, we're looking at our flip tensored with toss. So that's what those matrices look like. And again, the rule to actually do this, if you're doing on matrices with numbers in them, is you like squeeze this guy into there, squeeze him into there, squeeze him into there, squeeze him into there. The zeros give you zeros. The ones give you, a half times 1, 1, 1, 1, 1, 1, 1, and then you write it out all out flat, so you get this matrix here, okay? Make sense? Just how you do it. Doesn't matter. We're not going to actually really do that. Now, again, as I said before we said that not every state on a combined system has to be a tensor product of states on an independent system. We can have correlations just like that. An operation acting on composite system doesn't have to act independently on the subsystems, and therefore it doesn't have to be a tensor product of matrices acting on the individual systems. I know this might seem all boring. This is super important when we come to do quantum circuits, guys. This is like the difference between a single qubit gate and a multi-qubit gate. So if I might have an operation like this. I've just come up with something. Heads goes to heads, tails, and this is a deterministic process. It's perfectly well defined. Can this operation be written as a tensor product? If we try to factorize it, look, I'm not going to go into the details, but at the end we get heads times this thing, and we get plus tails times this thing. There's no way I can factorize this further. I have a different thing here and a different thing here. This is not a tensor product of two independent operations acting on the side. So this, therefore, this is an operation. You can see it here because in the subspaces of the matrix I have two different matrices, right? It's definitely not a tensor product. So this matrix creates correlations between the two coins. This operation creates correlations between the two coins. In the jargon we say it mixes the states of the subsystems. So now it's about time to drop the charade before I let you guys go take a break. Our tossed coin is an example of a classical bit with states 0, 1. We're not going to do heads and tails anymore because it looks ugly on the slides. We're going to call them 0 and 1. A bit string, the flip operator F is an operation called not in classical computing. I think you might have heard of it. And it's called X in quantum computing. A bit string like 0, 0, 1, 1, 1, 1, 0, 0, 0, 1 is a tensor product of classical bits, right? So now we know how to represent numbers. Since we knew about that, I forced you to sit through all that stuff about the tensor product. So now we know how to represent numbers in classical computing. And I want to end up by making the point that any useful computation is going to involve creating correlations between bits. Okay, it's going to take those bits, it's going to mix them together and produce outputs, right? And so useful computations have to be expressed in terms of multi-qubit operations. Okay, all right. Take a break, and we'll come back and do some quantum. All right. And if you have any questions that you were too scared to ask, come ask me now. We'll make it a 5 to 10 minute break, all right? I've kept to my time perfectly, by the way. I am amazing. I lost you.
That was easy. So I got lost a little bit.
You got lost a little bit.
No, but it looks like you understand all the stuff, so it's nice to watch.
Yeah, but I want you guys to understand it. How is it, Alex?
Basic things really easy. I was expecting a little bit more.
Okay, we're going to get to that.
Too easy for you? To be honest, I was expecting a point where you have a remote control with a bunch of buttons, and when you press it, you go into a parallel dimension, like the TV documentary that I saw, Quantum Leap. You've probably seen it, right? There's two guys, and there's one that goes in. That's not the subject of it. I'm very disappointed.
No, unfortunately, no.
Because that I understood.
Quantum communication is the thing that...
It was very interesting, complex.
Yeah, I know it's a lot, right?
Yes.
Nobody has to understand it all first time round.
Yes.
What I want to give people an idea.
It's not very good,
Yeah.
so it's really complex. But
That's all right. I want to give you guys a background so that you can go onto the Qiskit. I should have said this at the start. So you can go onto the Qiskit site after this and like make sense of what's going on the information they have there on the website. Right?
Okay.
Yeah. You don't like nobody's expected to. Like nobody when you go to a lecture in physics, right? You don't come away. You're there like, oh my god, what the hell is he saying for like an hour, right? But and you don't understand it all, right off the bat, right? It takes you go back home and you try stuff and then for about the third time you've been through material, you're like, oh okay, now I'm getting it, right? So especially I'm going super fast, right guys? I'm going very fast.
Yes, it's quite, when you're not used to it, it's quite like hard to understand at first.
Yeah, but like, I believe, I hope, or my idea is that you'll get enough of an idea of what these things are that you can, understand it and learn it.
It's kind of refreshing, especially for me. It's been 8 years since I graduated from college, so it's super refreshing. I just have one little request.
Yeah.
Can we get the slides afterwards? Not
Yeah,
now.
absolutely. Yeah, yes,
Yeah,
absolutely.
can I
We'll
give
send
you
out.
my email or something?
Yeah. I was going to say that. I was expecting to have sort of a small room and stuff to say, and I should have said at the start. Look, I'll tell you what I'll do. I'll put my email address on the screen. Hold on. This is a bad way to do this. No, let me. Okay, guys. Sorry, I should have said it at the start. If you want the copies of slides, either email Steph, all right, who's the organizers, right, or email me directly. Yeah. Okay. Perfect. Yeah. Yeah. So, and I expect, like, as I was saying, like, I don't expect everyone to understand everything first time, right? At the end, I'm going to give you I'm going to direct you to the place on the Qiskit website where you can get where there's and like there's a presentation of a guy who takes a very similar. Well, okay, let's face it. I copied him. His approach, right? John Watrous, and he has like an excellent series of videos, which, as I said, take the very super similar approach to the one I'm taking here, and take you on. You can go through it more slowly, right? And really, the explanations are super. Go.
Like during the course of the presentation, do we still get to know the practical uses of quantum?
The issue is right now there are no practical uses of quantum computing, right? There are some algorithms which are known, like Grover's and the quantum Fourier transform and above everything Shor's algorithm, right? But things like quantum Fourier transform and things like phase estimation, they're like little things that work as subparts of a program, right? Of a circuit. They don't. None of them in and of itself is useful. Hopefully we can compose them to make something useful. The only, really, it's like the only useful. Grover's you could argue is maybe useful, but not really. The only useful algorithm is Shor's. And what does Shor's do? Shor's factors large numbers exponentially faster than what you can do on a classical computer. Now, there's an absolutely useless thing to do unless you're trying to break RSA encryption. Yeah, which is so now the world needs to move off of RSA, right? And so then it's going to be useless again. Hopefully that happens before Yeah. So the big, to my mind, the big challenge is to actually come up with useful algorithms for quantum computers, because currently, according to me, there are some other, there are some things in terms of, there are some ideas about how you could use it to simulate physical systems. So, for example, in quantum chemistry, you want to figure out what the ground state of some molecule is, right? And then maybe that's something that the quantum computer can do exponentially faster and more efficiently than classical computing. But even those are a little bit unconvincing at this point. But they're probably the first things. It makes sense that simulating quantum systems is something that quantum computers are going to be especially good for, right? But we're not going to be able to get up to anything like that. That's like a lot harder. Anyway, so the answer to your question is no, because sorry.
So thank you. No, thank you.
No problem. All right, get going. Check 1, 2. Okay, perfect. So everyone, to address a couple of things I should have said at the start. First of all, I really want to emphasize, I don't expect everyone to be able to understand everything I'm saying right, today. That's way too much. If I go to a physics lecture, I understand at a 20% level, and then I go back home and I understand the rest, on my own time, going over stuff. I'm going to give you references, the book, Nielsen and Chuang, a series of videos from the IBM site by a guy called John Watrous, whose approach is, I've shamelessly stolen. And my goal is to give you guys the first impression so that you can make sense of, information from that, so that you can pick up Nielsen and Trong and start reading it, so that you can go and look at the information on the Qiskit website and make sense of it, and not be just like, oh God, this is so scary. What do all these bras and kets mean, right? I also meant to say right at the start, if you want the slides, either email me or email the organizing committee, and yeah, that's what he said. Yeah, so yeah, we'll do that. Okay, we filming? No, he said no. Okay. Yeah. Anyway, but let me say, like if you watch the series of John Watrous videos, they're obviously they're longer than 3 hours in total, but I mean, his explanations are, and he covers similar ground to what I'm doing here. Not exactly the same, but quite similar. Okay. All right. Now, how many people here, if I say the complex plane, know what that is? Half to 60% of you guys. Okay. All right. You other half, pay attention. All right. Steph, do you know what a complex number is? Okay, pay attention. So, complex numbers are much easier to understand than rational numbers or irrational numbers, okay? And they are much more beautiful. They're the most beautiful thing I learned in my mathematics degree. Complex analysis is incredibly, painfully elegant, and even just the bog standard quantum, use of complex numbers, complex arithmetic that we're going to do in quantum is also just, I mean, it's just lovely. It's so simple. All we need is this guy, right? A number which squares to -1. Okay, that's all. That's the only thing. And then we're going to say that we can multiply I by a real number, or we can add a real number to it. So if I have square root of -1, I can multiply by a number and have 2 square root of -1. Or I can have 2 square root of -1 plus 3. Okay, that's the basic thing something would need in order to be a respectable number. Okay? It has to be algebraically closed. And so therefore, this is a totally legit number. It has a real part and it has an imaginary part. Okay? All the real stuff gets added up, accumulated off into that side, and all the imaginary stuff gets accumulated off into that side. What does real and imaginary mean? It means nothing. Okay? They're the stupidest names ever. This number is called a complex number for absolutely no good reason. It's no more complicated than a rational number. It's way more simpler than a definition of a real number. Incredibly surprisingly, the complex numbers, as we've just defined them, are closed under all the usual operations of real number algebra. So, for example, addition. All right, how do we add 2 complex numbers? We have 1 plus I plus -2 plus 2I. Excuse me. We know how to add real numbers to real numbers, and so we get a real number there. Here, we know that I plus 2I, obviously, if this is going to be remotely sensible, that has to be 3I by, I don't know, the distributive law or something, just basic laws of algebra that we want to obviously work for complex numbers. And so what we get out is another complex number. And this works for all the other operations, right? I'm not going to go through them one by one, but you can see the course notes. The one that gets a little bit tricky is division. There's a trick, but it's a standard trick, and you can look it up. I had course notes, but you don't need to look. You can just ask ChatGPT. We're going to need the notion of the magnitude of a complex number, so the length of a complex number. So that's just you just treat it like a vector. You say a squared plus b squared whole square root. It's not how many times in your life. We're going to need a notion called the complex conjugate. Complex conjugate takes the imaginary part of the number and multiplies it by -1. We'll see what that means geometrically in a second. Why is this useful? Well, one of the things it's useful for is division. There's this trick with division I mentioned before, which I'm not going to show you because we're going fast. there is a useful relationship between these two things, between magnitude and complex conjugate, in that if z is a complex number, then z star, z complex conjugate, times z gives you the squared magnitude of the complex number. That's one you use all the time doing calculations. All right, now there is one way. I said the complex numbers are the best numbers, they're the most beautiful numbers. But there is one way in which complex numbers suck as numbers, right? And that is that we can't put them along a line. Okay? Which one's bigger, 1 or I? Don't know. Right? So they do not have a total ordering relation like all the other numbers. What we can do is we can interpret the real and imaginary parts as coordinates in a plane. This is called the complex plane. And everything, you know, when we think about complex numbers, we think about them representing points in a plane with an imaginary axis and a real axis. And that leads to the idea of expressing a complex number in polar coordinates, right? Instead of talking about the A and the B, the real and the imaginary parts, we talk about the angle of the number from the real axis and the length and the distance of the number from the origin. So we can write this. This complex number z equals the magnitude of the complex number times cos theta plus I sine theta. Who remembers which one's cos and which one's sine? Yeah. Cos is that one, sine's that one. Yep, exactly, right? So cosine is telling you the extension along the real axis, and sine is telling the extension up along the imaginary axis vertically. And this theta is this angle I talked about, right? So we can write a complex number that way. And this looks worse, right? Oh, shit. Until we do this. What are we doing here? We're expressing the function cos theta as a Taylor series, and the function sine theta as a Taylor series. Now the Taylor series for cos is 1 minus a half theta squared. For sine it's theta minus a 6 theta cubed, blah, 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 off to infinity. We rearrange the terms. So we have a term 1 here from cos, a term I theta here from sine, a term half theta squared here from, from cos. I'm turning this negative sign into an I squared here. And then I have this term here, which I'm turning this I here into I cubed. And that I cubed is I squared is negative 1 times I, and that gives me negative I there. Okay. And this Taylor series is the Taylor series for the exponential function. And so now cos theta plus I sine theta is e to the I theta. And so we can write our complex number in this form, that z is r e to the I theta. Now, so this r is called the magnitude, we already saw that. And the e to the I theta part is called the phase of the complex number. Okay, so very often you'll see in quantum mechanics people talking about a phase, all right? They're just talking about the angular part of the complex number, okay? Not the distance, the bit that goes round, the e to the I theta part. And in particular, some people get enormously excited over this, okay? If we set theta equals pi and r equals 1, we get this formula which relates e I pi minus 1. Now, polar form, why do we love it so much? It makes it extremely easy to multiply and exponentiate complex values, right? So, I mean, we're not really going to do this, but, you know, just to let you know why we care about this, if I have two complex numbers here, a e to the I alpha times b e to the I beta, then, you know, you just multiply the magnitudes and you add together the phases, the arguments, and and you get the answer, and that's way easier than multiplying out this expanding out the form. Even better, I'm not going to go into this. Even better, you trivially get out the fact that there are n distinct roots of any complex number, n distinct nth roots. And that is amazing. I mean, it's there. You can review it on the slides later. I'm not going to start getting into the details of that, but you can just verify it for yourself. Think about it. What we did was we postulated that there was a number that's the square root of -1. And almost immediately, what came out of that, after having done almost no work at all, we got that there are n distinct roots of distinct nth roots of any number. So we got a system of numbers which is closed under nth root. I mean, that's amazing, right? That's like completely unexpected. We have no right to expect anything ever to work out that beautifully. And these roots are arranged in a kind of evenly around a circle in the complex plane. And that's what we're going to talk about, complex numbers. Instead, we're going to start talking about quantum mechanics. And this is not a lecture about particle physics, but just to make things concrete and to make things quantum-y, I'm going to talk about electron spins. Electron could be any elementary fermion. Who knows what spin is? Yeah, it's an intrinsic property of the electron. What kind of thing is it? Yeah, it's an angular momentum, right? So angular momenta. I mean, okay, if we want to just delve, just get just a tiny bit of foot wet in particle physics. If you have a wave function which describes the position or whatever of the electron in space, there's a quantity you can form from that, from differentiating and multiplying that wave function, which is a probability current, like a flow of probability, right? And if you take that and you look at and you calculate that quantity, that flow of probability for an energy eigenstate of an atom or something, you'll find that, for example, the ground state of the hydrogen atom, which is spherically symmetric, has 0 probability current. But then when you look at the excited states, these P cells, they have a non-zero probability current, and that corresponds to the angular momentum, the orbital angular momentum of the electron in the atom. Okay? So we have orbital angular momentum, so-called orbital, right? Which is related to the flow of probability, right? When we're talking about spin, we're not talking about anything like that, right? We're talking about some abstract quantity born out of geometry that's an intrinsic property of the particle. All electrons have spin half. And so orbital angular momentum comes in quantities, comes in packets of h bar, all right? So you can have 1 h bar, 2 h bar, 3 h bar. And that's the same for gauge bosons, like photons. They also come in integral packages. Fermions, matter particles, come with quantities of half h bar. Okay, so point is, I can measure an electron spin, and what I find, if I measure the spin in the vertical direction, its angular momentum in the vertical direction. You can look up the Stern-Gerlach experiment, Stern-Gerlach or something like that. Where they did something with magnets and silver atoms. It has to be silver. Anyway, I'm not going to get into it. And what you would expect to find is, you imagine these electrons coming through. They were atoms, but that doesn't matter. They have a single unpaired electron in the outer shell. So you can imagine these atoms coming in with any orientation of angular momentum, and you imagine the ones with an orientation like this would not be deflected by this magnet, and the ones with that would be deflected a lot, and then the ones with this would be deflected something. And no, you do this experiment, and what you find is that no, what you measure is always plus or minus h bar. Okay, so they form this the basic behavior you get. That's why it's called quantum mechanics, because things come in quanta. So an electron spin, we can measure it up or down. And so therefore, just like, look, we get something that looks a whole lot like our heads and tails experiments, right? We can write the state of an electron spin as some probability times up plus some probability times down. Now here's where it gets different. These are going to be complex numbers. So this time these coefficients aren't probabilities, and they're not even real. Quantum states belong to a complex vector space. So this is the difference. This is the first difference we're going to encounter between quantum mechanics and classical probability theory, is that now these are complex numbers. And they can't be probabilities, because probabilities can't be complex. To get a probability out of this state, what we do is, did I skip a slide or? Oh yeah, okay. So an inner product no longer produces a probability like they did before. We said they produced a probability before, but a complex number, and the word, I don't know if the word makes any sense at all, but the word is used is called an amplitude. So these inner products, the basis state with the state is a number called an amplitude. And to get a probability out, we take the squared magnitude of it, okay? Which is the same thing as multiplying it by its complex conjugate, okay? So probability of up is the squared magnitude of the coefficient of the up state in its expansion as a vector in the basis, in the up-down basis. Was that absolute nonsense, what I just said? It's just all the same as what we were doing before, except before, these coefficients in the expansion of the representation of the thing as a vector were probabilities. Now they're not. Now they're complex numbers, which we have to take, squared magnitude is the number times its complex conjugate, okay? Gives me a real number. It's squared magnitude. Now, in a complex vector space, previously we said that the relationship between Bras and Ketz was transposition. In a complex vector space, that is no longer the case, and instead we have this thing, this dagger, is the relationship between Bras and Ketz, and it's the conjugate transpose, because what it means is transpose the matrix or vector and complex conjugate every element. This is a basic operation which is very important. It's the equivalent of the transpose for a real vector space is the conjugate transpose or the adjoint operator, the dagger. Usually we just pronounce it as a dagger or whatever. And now, I'm not sure if I wrote earlier that inner products are symmetric, but I think you know that from high school. This is not the case in a complex vector space. In a complex vector space, they're almost symmetric, but because they're a complex number, you actually get the complex conjugate out. Remember that transposition reverses the order of matrix multiplication. So if you have AB transpose, that's B transpose A transpose. I think I'm saying this right. And the same thing happens with the dagger, the adjoint operator. Another thing that you will see physicists do all the time is to say that a complex number is the same as a 1-by-1 matrix holding that number. Okay, so we very often treat Z conjugate and Z dagger as the same thing when we're doing calculations. It's just convenient. If you have an inner product, oh well, that's the same as daggering both those things. And no big deal. Oh, yes. I suck at this. Now, previously we said that there was a condition on what makes something a legit probability distribution, that the probabilities have to sum to 1. Here we have a different condition. Probabilities have to sum to 1, but the probabilities are not the coefficients. So what we get is that these things are the probabilities, the squared magnitudes. The squared magnitudes have to sum to 1, which is exactly the same thing as saying that the state vector has unit length, Euclidean length. Okay, which is nice. That's a nice property. Right? It's actually really nice. It has a very nice geometric interpretation. Vectors have to be on this unit ball or whatever. Okay, Now we're going to do this. Somebody tell me what a matrix is. What's the best way of thinking of what a matrix is? All right. So when yes. It is a linear transformation or mapping or function from one vector space to another vector space. That's what you're saying, right? Yeah, yeah. So what is it? It's a linear function, okay? That's all. That is why matrices are so important. They are the set of the field of matrices corresponds exactly to the set of linear functions on vector spaces, from vector spaces to another, okay? I know in high school your teacher taught you something to do with solving linear equations, and yeah, it's related to solving, yes, you can use them to solve linear equations, all right? But that's not what they are. What they are is linear functions, linear mappings, linear transformations, okay? So, how many people know how to find the eigenvalues and eigenvectors of a 2x2 matrix? Yeah, I used to. Oh, used to is good enough. Used to is good enough. So some people, okay, all right. So a matrix is a linear transformation of space. One of the first things we're going to ask in order to understand what sort of a transformation it is which directions in space are left invariant by these transformations. Okay, which directions are just scaled by a number. And these directions are called the eigenvectors. So in our notation with Ketz, we're going to label these eigenvectors lambda because there is going to be some discrete number of them, or in a discrete vector space, in a finite vector space. So we have submatrix M here, it doesn't matter what it is, and applying M to its eigenvector is going to boil down to multiplying that eigenvector by a complex number. And geometrically, you can think of that. If I have that eigenvector pointing somewhere in space, and I hit it with this transformation, then all that happens is that eigenvector gets scaled, right? Okay, it's a complex vector space. That's a little bit hard to visualize because multiplication by complex numbers is a bit. Anyway, so let's look at these two matrices. They look pretty different, right? Staring at them, you can't really say there's much. It's pretty hard to spot that there's anything similar about them. This guy, if you figure it out, his eigenvectors are 0 and 1 are the basis vectors, and his eigenvectors are, we'll come back what those things are linear combinations of the basis vectors. If you calculate it, you find that they have the same eigenvalues. So it turns out these two matrices are essentially, in some sense, exactly the same matrix, exactly the same operation, but written in like a rotated basis, written in a different basis. Okay, so instead of using these guys as your basis, you've picked these guys instead. So in some sense, they're the exactly the same matrix, just kind of just rotated around a little bit. And clearly the first representation is far more transparent and far more useful because we just see, okay, this matrix multiplies this direction by 2 and multiplies the other direction by 3. Okay, so this is far more informative, more useful basis to have chosen to have written our matrix in. Physicists spent a huge amount of time trying to find a way to diagonalize matrices, right? Trying to find a basis where the matrix is diagonal, because in that basis, the evolution of the quantum state is very easy, is very trivial. It also tells you immediately what the ground state is and all that. Now, the eigenvalues of a matrix. Wait, did I skip a slide? I'm going to tell you a second fact. I think I have a proof, but we're going to skip over it. The eigenvalues of a matrix are real if the matrix satisfies this property. Okay, it is equal to its own adjoint. Okay, if I dagger it, I get the same matrix back. Obviously, that's going to be the case for any symmetric real matrix, but it's also the case for some other matrices with complex elements. And we call this kind of matrix, which just satisfies this property, as Hermitian, or self-adjoint. This is the proof. It's easy, okay? But we're not going to do it, but it's there on the slides. It's easy. You can puzzle it out and understand what I'm saying there. There's a second wonderful property of Hermitian A matrices is that they have orthogonal eigenvectors. So their eigenvectors are always perpendicular to each other. It's a wonderful property. Oh, sorry. Excuse me. More correctly, we can choose them to be orthogonal. The reason for that is that if you have a matrix that has a repeated eigenvalue, then within that subspace of the eigenvectors, it's an arbitrary choice of eigenvectors and blah 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 blah. But you can pick it. You can pick a set of eigenvectors which are orthogonal to each other. Again, proof which we're skipping. So if you have a Hermitian matrix, you can find an orthonormal basis for the vector space where each basis vector is an eigenvector of that Hermitian matrix. And the matrix itself is diagonal when written in this basis of its own eigenvectors. Just like that 2, 3 one we saw before, okay? We've picked a basis where the basis vectors just get scaled. Tell me I'm not making any sense. What's the difference between these matrices? Yeah, both symmetrical. I haven't even noticed that. Oh yeah, I made this one up. But yeah, it's got to be symmetric because it's real. It's real and Hermitian. Yeah. It is symmetric. Yeah. I've said that I've told you guys. I know it didn't prove. I know it didn't show it very clearly. But I've told you guys that these have the same eigenvalues. They're somehow the same matrix related by a 45-degree rotation, I think, of their basis, of the basis we're writing them in, okay? We've picked, instead of picking the basis that goes like this, we've picked the basis that goes like this, okay? And we're writing it in that in the basis of those vectors. In this basis, the matrix is diagonal, which means that when we apply it to any basis vector, we just scale that basis vector. That's not the case here, right? If I take a basis vector 1, 0 here, and I multiply, I get 5 times, and I get minus 1. I'm not just scaling it. I don't just get the same basis. I don't just get the same basis vector scaled back. Okay. So here, and what is it? I mean, obviously, if I'm just scaling the basis vector, that makes the basis vector an eigenvector. Okay. So I've just turned the argument around, right? If it's diagonal, then the basis vectors have to be eigenvectors. Does that make more sense? She's nodding her head, so. Does that make more sense? Okay, all right. So the point is, diagonalizing a matrix is about finding a basis where the matrix is diagonal is about just finding the eigenvectors, using those eigenvectors as a basis. We can only do that trick for normal matrices, but for Hermitian matrices, okay? And that leads us to spectral decomposition. I'm putting that formula up there because it's gorgeous and beautiful, and it says that this matrix can be written in this way, but don't worry, we're not going to use that formula. Okay. If that was a lot, go to this website called youtube.com, and a guy called 3 Blue 1 Brown, who has the most beautiful videos which explain linear algebra far better than anybody can possibly explain, because he's genius animator and like he just makes it so easy to understand, right? I can't do it. You know, I can sit here doing this right, but I can't do it as well as he does. But this is incredibly important, and it's worth your while learning all this stuff because this even comes up in machine learning and all this stuff as well, right? This isn't, you know, this isn't something that's specific to quantum. What's specific to quantum is the effect of it being a complex vector space. Okay, let's move on. I took too much time on that. All right, we're going to use this. So we've said that the states spin up and spin down. Determine the spin measured in the vertical direction. We've said that you can only that if you measure if you have an electron in space spin up and you measure its spin, you get spin as plus a half. If you measure spin down, you get spin as minus a half. Okay. Make sense? Yes. I'm getting nods. Okay. Good. Sorry. Excuse me. In units, in sensible units, where h bar equals 1. Okay. So somebody asked me. Last time, what did people ask me? Oh, what's h bar? H bar is the scale of quantum mechanics. Okay? As I said, it's... Yes? Yeah. H bar is just a number that comes out of Planck's yeah, but it's not... I don't think there's anything which says that things have to be... I mean... It's not like if you measure the things get quantized when you like a memento or whatever get quantized when you stick them in a box, right? It's not that h, but yeah, for angular momentum it's weird and interesting because it's always a half integer multiple of h bar, but that's not general, right? If you look at particle in a box, it's not so simple. There's a length in there, and I forget off the top of my head. I don't remember what it is, but it's not like everything. All numbers always come in quantities of h bar. Yeah. In angular momentum is kind of special, right? I hope I didn't say anything wrong there. We'll verify. We'll look it up. We'll on ChatGPT and ask him what the energy of a particle in a box is, and I think we'll see it. Right? So yeah, so anyway, the point is we're going to choose sensible units. Okay. Sensible units for microscopic things, not units that engineers use, and h bar is going to be equal to 1. Otherwise, we would have an h bar in it. All right, and we want to ask, we're going to tackle this. We want to find a way to represent observables in quantum. I said, I said kind of at the end of the section about classical, I kind of said, well, if you want to, you could think of the expectation of observable in classical as some kind of vector that we inner product with the state, right? And I'm going to tell you that is not going to work in quantum. All right, quantum is way more interesting than that. So let's see how we get. So I want to take us to arrive at that rather than just asserting. If you look in any quantum mechanics book, this is one of the postulates, and it'll just write down the answer. But I want to get there, right, by a journey, right, by taking a meander, right. So we want to ask, okay, how can I we think about averages and expectations. How can I calculate the average spin for an arbitrary state of an electron in this, vector space? All right. Well, we're going to start by the definition of expectation of average in classical probability theory. The definition of an expectation is it's the number times the probability of getting that number, yeah? And sum over all the possible numbers we could get out, yeah? Tell me yes. Right, good. Whew, we got that much. Here, the numbers we could get out are plus half and minus a half. And I said that the probabilities are these squared magnitudes of the coefficients and the expansion in the up down spin down basis. Okay, maybe I'm confusing everything by drawing like little arrows everywhere, but this is saying something no different to, this is just the definition of an expectation in classical probability of theory. I'm multiplying plus a half times the probability of getting plus a half, which is the squared magnitude of psi up, negative a half times the probability of getting psi of getting negative a half, psi squared magnitude of psi down. And if you kind of squint a bit, that looks sort of a little bit like an inner product of psi with itself. I'll show that on the next slide, I think. But then it has these weird numbers in there, which is kind of messing it up. well, maybe we can throw a matrix in there, right? And maybe that'll make us get our weird numbers out. So let's say the spin, our representation in quantum mechanics of spin, vertical spin z in the z direction, is like this matrix, and then we'll sandwich it between these between the state, within this inside the state, which will give us that quadratic. You know, the point is that we're trying to reproduce this. This squaredness of it, this quadratic nature of it, right, which we didn't have before. And that we're getting out of sandwiching SZ between the bra and the ket. So what matrix would it be? Well, in this case, let's try with this diagonal matrix. SZ equals a half of 1 minus 1. This is also going to be our friend, this matrix. And let's show you that this works out. Okay, let's go through it bit by bit. Wake up, follow this. We have a sandwich, bra psi, ket psi. So bra psi is the conjugate transpose. So we take psi, we stick it on its side, we'll lay it down horizontally. We conjugate both each of its elements, multiply it by the matrix. We said we're going to try, I told you is a good one, a good guess. And then we have ket psi, the column vector psi. All right, so let's multiply this out. We get 1, 0 times that. We get psi up. Negative 1, 0. We get psi down. We get psi up, psi down. Psi up, negative psi down, sorry. Multiply that. We're going to get psi conjugate. Blah, 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 blah. We have a half there. You see that works out, right? Anyway, you can do it. It's matrix multiplication. It's easy. And then remember that this psi conjugate times psi is the squared magnitude of psi, and that's the thing that we were hoping to get. Okay, so in this case, a diagonal matrix sandwiched between the bra and the ket gave us the expectation value we were looking for. So let's so now we have our first quantum observable, SZ, which we can write as a matrix in this, high school matrix notation, or we can write in the Dirac notation as the outer product of up with itself. This is, this outer product here is this element here. This outer product here is this element here, and we have 1 and minus 1 and a half out the front. Now, who can guess what SZ applied to? Tell me what SZ applied to the spin up is going to give me. SZ times the matrix, but times the state up. State up is the state 1, 0. 1 half up, exactly. 1 half up. What kind of a vector is that? Is up. It's an eigenvector. Do the same with down. What's SZ times down? Minus a half down, right? So it's also an eigenvector. So up and down are the eigenvectors of the SZ operator. Well, that's what we knew, right? We knew that going in. These represent that state and that state, okay? They are states of definite vertical spin, okay? So they're the eigenvectors. Good, perfect. So this works. This is working out nicely. That was the calculation I just asked you guys to do in your heads. You can see it. It's easy to see, right? I have an up here with an up there. That gives me 1, so I get a half there, survives. Here I have a down with an up, so that dies. Here I have a down with an up, so that dies. This survives, and I get minus a half, right? Okay. And so they're the eigenvectors. And the corresponding eigenvalues, if you notice, of plus a half and negative a half are the observable possible values of spin. And so therefore, oh God, okay, I have more. Now let's skip ahead. Oh no, let's not, okay. Okay. And from this we can very quickly also figure out we're going to skip this. I don't want to do that. So now we ask, now we've said we've got in our head this connection of observables with matrices, which we didn't have before. We certainly didn't have that anything in classical mechanics. For good reasons we didn't have that in classical mechanics. So this doesn't happen in classical mechanics. So which matrices are we going to allow? You might ask, well, maybe the diagonal matrices? You can probably guess that that's not going to be the answer, right? Why wouldn't it be diagonal matrices? Well, I've already said that just by change of basis, we can turn a matrix which is not diagonal into diagonal, right? Into diagonal matrix. So which matrix is going to easily diagonalize? Well, the answer is, what the real restriction is an observable number, a measurement we can make in physics gives me a real number back, not a complex number. But our quantum states have complex elements, so what kind of matrix is always going to give us a real number? Well, guys, I already told you the answer to that. What kind of matrix gives me a real number back? Self-adjoint, a Hermitian matrix. Yeah, exactly. So Hermitian matrices represent observables. Okay, let's stop. I hope that was a helpful walk towards the answer, but if you just want to know the answer, this is the answer, okay? And this is most physics, most textbooks on advanced quantum mechanics will just present this, okay? An observable is a Hermitian matrix. The observable values are its eigenvalues. States with a quantum state with a definite value of the observable is an eigenvector of the Hermitian matrix. And any other state, which has got to be a linear combination of the eigenvectors, right, is a superposition of the eigenvectors or the eigenstates, I say sometimes. The probability of an eigenvalue associated with a given eigenvector is the squared amplitude of the coefficient of that eigenvector in the expansion in the eigenvector basis of the Hermitian matrix. I think some people understood what I just said, but it's just if we take the quantum state, we expand it out in terms of the eigenvectors of the Hermitian matrix, then it has certain coefficients, and the probability of getting that result, spin up, for example, is the squared magnitude of the coefficient on the up basis vector, up eigenvector, okay? And expectations are sandwiches of the matrix inside the state. So now we finally get to what is it that makes quantum mechanics quantum mechanics. And this is the famous experiment, all right? Take an electron that's got its spin pointing up. We just measured it. And now let's measure its spin in the horizontal direction. If I'm a classical physicist back in the, back before the 1920s, what answer would I expect to get? No, this electron's there. It's spinning around. Nothing's spinning, by the way. It's like an intrinsic quantity it's an intrinsic zero, exactly, right? That was what one would classically expect for an something. If the Earth's spinning around this north-south axis, then its spin around that axis is zero, no? So we measure in the horizontal direction. Classically, we expect to measure zero spin. What we actually get is that with probability 1/2, we get +1/2, it's spinning in that direction. With probability 1/2, we get -1/2, it's spinning in that direction. The fuck, man? So we know the vertical spin exactly. We have zero information about the horizontal spin. And then if we measure the horizontal spin, then after that we have no information about the vertical spin. Okay? So as soon as we did a measurement in this and this, then suddenly we lost any now this is in just an equal superposition, a completely random state of. It is not because you disturbed the electron by making a measurement. Okay? That is an incorrect statement which you will sometimes see made. Okay? We're going to see why it really is. All right? So obviously we want to represent this spin Sx as a matrix. Let's go with this matrix. I don't know how. I'm putting it up there. All right, just go with it. All right, it's gonna work. I can't motivate that. Which is the same as this. Now let's calculate the vertical spin for up and down. We're going to calculate the expectation value. Let's do this. All right. We notice, first of all, that Sx times up, applied to up, is a half, down. Let's see why I'm making that claim. All right, if I have an up here, if I apply it to an up, this term here survives and I get down. This term here vanishes. Now let's consider, I did up, let's consider down. If I have a down here, then this term here vanishes, and this term here survives, and I get up. Okay? So the action of this matrix on the basis states up and down is to exchange one for the other. Okay? We already saw this matrix before. It was the flip a coin matrix. Okay. So we have these two properties, all right? So now if we calculate its sandwich, we apply this to there, we flip it, and this is 0. Similarly, its sandwich on the down state, its expectation value on the down state, this gets flipped up, that's 0, and that's 0. So that's nice, okay? That's at least some sort of a sanity check, right? That if we calculate if we measure spin, horizontal spin, on an electron which is in spin up state, we will get a 0 expectation value. Not a 0 value, we know we get a plus or minus a half. We get a 0 average value, okay? So that's good. Now our next task is, well, what are the eigenvectors in terms of, of this spin, horizontal spin observable? And you can easily verify that these are the characters we're looking for, okay? If we take Sx and apply it to this, what's going to happen? Sx applied to this guy, what happens? Sx applied to up is half down. Sx applied to down is half up. And so we're going to get back a half times 1 over square root 2 of down plus up, which is the same as up plus down. And so this is an eigenvector with eigenvalue 1/2. This one, do this one for me. Sx applied to up is down. Sx applied to minus down is half minus up. And so what I get here is what I'm going to get here is 1/2 of 1 over square root 2 down minus up, which is negative a half of 1 on square root 2 of that vector. And so its eigenvalue is negative. It's an eigenvector with an eigenvalue negative a half. Okay? That make sense? No, obviously not. Just trust me. You guys can do it. It's easy. The action of Sx on these basis vectors is to flip them, okay? And because I have a negative sign here, yes? To be like, because that's what works. Nothing other, yeah. I mean, we didn't have to choose that one. We could have chosen, there's another one which has minus I half, and that one also works. But we usually use that to represent the spin in the y direction, there's 3 directions. Yeah. I'll come to a second. I can give you a better answer than that in a little bit. Okay? Yeah. But yeah, for now, it's a matrix I pulled out of my butt and put on there, and then we discover that, hey, it has eigenvectors which are that it has the properties we're looking for. It has 0 expectation value on the states up and down. It has these other vectors which are these eigenvectors which we're going to call left and right that also have spin, that also have eigenvectors, eigenvalues plus minus a half. A two-level system, yes. A two-dimensional vector space, yes. No, but there's not. That's what makes it. That's the point. Yes, that is exactly the point. That is precisely the point. That it's not a four-dimensional vector space. I can't say, right, that is precisely the point. That let me go on a little bit, and I think it's going to be better once I get a couple of slides ahead. But then ask the question again if it still doesn't make sense. No. Sorry, nada. Oh shit! This has run out of battery. That was my fear. Damn. All right. Why are matrices different? You know, in classical we have like numbers. Where suddenly we've got these matrices. Suddenly observables are represented by matrices. We didn't have that in classical physics. Why is that important? Well, first of all, you know, one huge difference between the algebra of matrices and algebra of numbers is that matrices don't commute. Matrix multiplication doesn't commute. So a quantity that physicists often care about is a commutator, often calculated commutator of two matrices, right? It's the difference between AB and BA. So let's compute this quantity for SE and SX. And this is straightforward, right? We have, you know, 1 minus 1 times 1, 1, 1, blah, 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 minus that. You can follow it through, and what we get out is some matrix here which is not 0. So that's telling you the important point is that SX and SZ do not commute. They represent incompatible observables. Observables which are represented by matrices which do not commute are fundamentally incompatible. Let me not get too far ahead of the slides. Are fundamentally incompatible, and we can't have knowledge of both observables at the same time. So the classic one, which you will have all heard in any description of quantum mechanics, is momentum. What am I doing that for? Momentum, I don't know. And position. So exactly the same thing arises in particle physics and quantum mechanics for position and momentum. They are operators which do not commute, and therefore we cannot have perfect information about the position and the momentum of a particle at the same time. Okay, they are incompatible observables. Now, let's see what that means in terms of vector spaces. If this is a fact of linear algebra, which I'm going to put on there, and I hate not being able to prove it to you, but I'm not going to. If the commutator of two matrices vanishes, then the eigenvectors of the Hermitian matrices can be chosen to be identical. So that means we can diagonalize both these matrices simultaneously, okay? We can pick a basis in which both these matrices are diagonal. And that means we can know the values of, what are two things which do commute? I'm blanking out on what is an example. I don't know, spin and 2 times spin, right? Those matrices commute. It's just 2 times the other one. And so we can know both those quantities, both those observables perfectly at the same time. They're compatible, right? As long as the matrices commute, we can diagonalize them we can find a basis in which they're both diagonal. If they don't commute, then it is a fact, a mathematical fact of linear algebra, that no such basis exists. And so if one matrix is diagonal, and so we have, you know, we have definite values of its state in those basis vectors, then the other one is not diagonal. And there is uncertainty around that, and when we're in a basis, when our state is an eigenvector of that matrix, so it's definite, it has a definite value for the observable, then the state is not an eigenvector of this other matrix, and its state is a superposition of values of the observable. I know this is hard, what I'm saying now. So I don't mind saying it 5 times, okay? Because this is the critical thing. This is the critical point of what makes quantum mechanics different. So if they commute, they have the same eigenvectors essentially. They're diagonal in that basis, and the observables are compatible. Otherwise, if they don't commute, the matrices don't commute, we cannot express them in a diagonal form in any base, both simultaneously diagonally any basis. And so they're incompatible in the sense that if we have a definite value for one of them, spin up, down, vertical spin, then we do not have a definite value for the other one. All right, just as we saw, right? Okay, start asking. Yes, please.
It's a mathematical limit or it's a physical limit?
It is both, but yeah, it's assuming. So the way you do quantum mechanics is you have these postulates, right? The postulate is observables are Hermitian matrices. The values of observable values are the eigenvalues of the Hermitian matrix. And from there, purely mathematically, because of the properties of linear algebra, right, you discover that it is possible that you could have two observables which cannot possibly both be in an where you cannot have a state which is an eigenstate of both of them simultaneously. I mean, the model's not wrong because experiment tells us it's correct. I mean, the model's wrong. I mean, you can do quantum field theory and then spin is a totally different thing. Depends what sense of wrong you mean. The postulate arises out of the results, because this is the way we can explain the results of experiment. Okay, could there be some other way we can explain the results of experiment? Oh, there certainly are, right? Yeah, I mean, quantum field theory. Okay? But this is quantum mechanics, and it's all we need for explaining non-relativistic physics. Okay, or we've never found any contradiction in non-relativistic physics. For relativistic physics, okay, this stuff doesn't work anymore. Why? Because once you go to those energies, the number of particles is not fixed. If you start colliding electrons at relativistic energies, your number of particles, you start producing particles, okay? But for non-relativistic physics at low energies, quantum mechanics is sufficient. Does that answer the question or not? Yeah? Yeah. I don't know what it says. Is there some, what is the observation I can make of the world to say that observables are Hermitian matrices? Well, I mean, it's the Stern-Gerlach experiment, nothing more than that. This is what we observe, and this is the best mathematical model and simplest mathematical model you can come up with, which reproduces the results of the Stern-Gerlach experiment and millions of other experiments that have done in laboratories every day, right? We can't prove it's a postulate. It's a postulate which explains, which gives us out of which flow predictions which are validated in laboratories every day. Yeah. Oh, okay. And so this leads to this famous thing, the uncertainty principle, which I'm sure you've all heard of, which is that the product of the, this is standard deviation, essentially, okay? The square root of the variance of two observables is always greater than or equal to half times the magnitude of the expectation value of the commutator. So if they don't commute, then this commutator is non-zero, and so its expectation value is non-zero in whatever state, and so its magnitude is greater than 0, and so the product of the uncertainties in these two observables, whether they're position and momentum or spin up and spin down, is always greater than 0, okay? This is actually quite straightforward to prove, and if you look on page 89, I think, of Nielsen and Chuang, we have this extremely short proof, which, as your exercise, going home after this, right? You can try and understand this proof. There is a couple of points I want to make. Okay, first of all, they use the anti-commutator there. You can look up on ask ChatGPT what the anti-commutator is, and then convince yourself that this first equation is correct. They use something called the Cauchy-Schwarz inequality. You do not need to prove that yourself. Just look it up. It's an equality about that's valid in vector space and Hilbert spaces. Okay. Then the last step, the trick is that last step should be fine. Just see how that follows from what you already have. And then here at this last step, they're asking you to substitute in A equals something and B equals something that look like they don't make any sense at all, right? Because we have matrix equals a matrix minus a number, an expectation value. But when physicists write a matrix equals a matrix minus a number, what they mean is a matrix equals a matrix minus a number times the identity matrix. Okay? So if you then substitute that into what you have in the previous thing, then you should be able to get this result come out, which is Heisenberg's uncertainty principle written in its best, prettiest form. And if you can understand that, then you know that's going to be great. Very famous result. Let's take another break. I went a bit long that time. Again, if the discussion of observables and was unclear, come ask me. We'll go through it again, okay? Come ask me in the break.
I was thinking, like, if you take relativity, for example, you have
If you take what?
relativity.
Okay,
General relativity.
Just relativity is enough, yeah.
And they say, mathematically, they say you can deduce the Big Bang, because if you follow up the equation, then you find that there is a Big Bang at some point. But we don't have actual observation of the Big Bang. And is it the same kind of thing for this impossibility, or do we have like actual experiments that confirm that it's likely not possible?
I think it's a little different. I mean, the reason we can't observe the Big Bang is we have this thing at redshift 1100, which is the last scattering surface where the cosmic background radiation, where we can't see any backward because that's where it starts scattering. That's a limit to our ability to observe things. Here, I mean, if you believe quantum mechanics, okay, I mean, I guess you're not required to believe quantum mechanics.
Yeah.
But if you believe quantum mechanics, I mean, what is quantum mechanics? Quantum mechanics is that theory which says that observables are Hermitian matrices, okay? It then follows as a mathematical, if you believe that theory which says observables are Hermitian matrices, it then follows as a mathematical necessity that you can have observables which can't have definite values simultaneously. Okay? That's the kind of the best statement I think I can make about it. Are you required to believe in quantum mechanics? No, except that you would be a bit silly not to, given the incredible level of experimental evidence for it. I mean, look, dude, we do it. We have actual quantum computers. There are actual qubits, and they behave like they're supposed to behave, right?
And, but a good example actually. Those quantum computer, does they require that property to work? Like
yes, we're going to see that. Yeah,
okay.
So that's one of the points I'm going to get to is that if quantum computers are going to do anything useful, and by useful I mean do something that classical computers can't do, then that has to come from that property, because that is the property which is different. That is the thing which classical probability theory doesn't have.
Fermi-Dirac statistics without quantum mechanics?
No. Fermi-Dirac statistics are fundamentally a quantum thing, I think. Yeah.
So you don't
I mean,
you
although,
don't have nuclear reactions.
but
Without them.
but notice that as I understand it, Fermi-Dirac statistics are an independent postulate of quantum mechanics. The spin statistics theorem, I believe. Here's something. When I asked my my quantum mechanics lecturer, he wasn't certain about this either. My understanding is that you can derive the spin statistics theorem in quantum field theory. Okay.
I don't understand anything about that. Never heard. I heard that it exists. I don't know what it is.
It says that bosons.
Yes.
How to express this in the right way? That for bosons being things which can occupy the same quantum state at the same time.
Yeah.
Have integer spin, and fermions have half integer spin.
Because they can't occupy the same quantum space.
Yeah, right. So
it has to derive from that because it's talking about half spins.
No, it's an independent postulate, right?
Okay.
Of quantum mechanics. Of quantum mechanics.
Long ago?
Yeah. I know. No, but what you can do, I believe, and I'm not sure about this. Okay, and I've searched for the answer to this, and it's not easy to come up with. And as I said, my advanced quantum mechanics lecturer didn't know the answer. It's on to ask some of my particle physics lecturers, but I believe you can derive this. I think it's the spin statistics theorem because you can actually prove it in quantum field theory.
Okay.
Because in quantum field theory, bosons and fermions and spin and stuff isn't just this thing you hand add in, right? Spin in quantum mechanics is this degree of freedom where you go, oh yeah, and electrons have spin, okay?
Yeah, for no good reason.
For no good reason, right?
Yeah.
In quantum field theory, it's not like that. In quantum field theory, there are only certain mathematical objects which transform correctly under a Lorentz transform, okay?
Sorry,
and they are
is relativistic.
Yeah,
Okay,
right.
thanks.
Quantum field theory is another way is relativistic quantum mechanics, okay?
It's been a while.
Yeah, I know. So there are only certain mathematical objects you can construct which have sensible transformation rules under Lorentz transform, okay? One of those objects is, gauge bosons, right? So photons and stuff.
Mm-hmm.
One of those objects is fermions,
Okay,
right? So electrons and quarks and neutrinos. One of those objects is scalar, those are vector fields or spin one fields, fermion fields or spin half fields. The other kind of object is just scalars, right? Obviously they transform because they don't transform. They transform correctly because they don't transform. They trivially transform. And so what's the scalar field that we have in particle physics? Higgs field.
A scalar field in particle physics?
The Higgs field.
Sorry?
The Higgs field. Higgs boson. Yeah. It's a scalar field, a complex scalar field. It's a two. Yeah.
The problem with field is that. Okay, I mean.
Yeah.
Okay, there is a scalar field around me.
Yeah.
Okay. So sorry.
Apparently.
It's very hard to internalize.
Yeah.
It's like. I'm also coming here to ask a question regarding the X spin.
Yeah.
Matrix observation matrix. I groked at once the Z spin because it's half now.
Right. Yeah.
But I don't understand why the question I asked earlier is that okay, you chose a matrix that did not commutate.
Yes. That doesn't come. Yeah.
Why? No, I mean, why that one?
Okay. I actually still haven't got up to the section. Yeah, but we're in the section.
Is this due to observation?
It has the mathematical properties we need to produce the results of the observation.
Okay.
Yeah. But these are special matrices. These X, Z, and their friend Y form a basis for the vector space of a Hermitian 2 by 2 matrices.
Oh, the three of them?
Yes.
Oh.
Okay, we're going to meet them in a second.
On the
Okay. Yes, that's right. Yeah, it's a.
You just need three
because
matrices?
you have X, Y, Z. Yeah. So they form a basis of. Let's count degrees of freedom. We have 4 by 4. 2 by 2 matrix has 4 complex numbers in it. It's conjugate symmetric, which means that we lose one of those.
So
it's self-adjoint, so we lose. So they have to be real along there. So we have a real number there, a complex number there.
okay.
Oh yeah, sorry. Together with the identity, there's 4 degrees of freedom. Yeah.
Only 4?
Yes.
Maybe
No, let's go through
Sorry,
it again.
for me a complex number is 2.
Yes, yes, look.
So we got 8 degrees of freedom for
Yeah,
starting.
yeah.
So you remove one for the factor.
I removed two real numbers, one complex number for anti-symmetry.
Okay, so we get 3 degrees of freedom.
Symmetry or
You
anti-symmetry?
said two real and one complex.
Symmetry. Yeah, yeah. So now we're left, and these ones on the diagonal have to be real because it's conjugate symmetric. It's conjugate symmetric.
So it's 3.
So we have 1, 2, 3, 4.
Okay.
The 4 degrees of freedom are the identity matrix, X, Y, Z.
Okay, so the identity matrix is okay.
Yeah.
It's not complex, it's complicated.
Yeah, it's a little bit complicated. Anyway, yeah. So we're going to make those matrices. So that's the reason. Is that in a space of 2 by 2, in a two-dimensional vector space,
Yes.
you can only possibly in the what is the name for the space of 2 by 2 matrices in the space of matrices on a two-dimensional vector space.
Yes.
That is a 4-dimensional space. Yes.
Because there are 4 numbers.
Yes, that's a 4-dimensional space with a basis which is the identity X, Y, and Z. Yes.
So the identity is
Not because you have 4 numbers. You have sorry. The space of Hermitian matrices on a two-dimensional Hilbert space.
because it's
Because
Hermitian,
Hermitian-
so it's complex. 2-dimensional because it's 2 by 2. So you got 4
Yeah, it's a
numbers.
two- it's
you
two-
have 4 complex numbers that become 8. 4 real parts and 4 imaginary parts.
Yes.
Right.
But then because it's Hermitian, it has to obey A equals A dagger.
Yeah, correct.
Yeah,
So
and
it
that
means that
reduces your
you
degrees of freedom
lose
to
3,
4.
You
Yeah,
lose
you
3
lose
no, sorry.
4. You lose 1, 2, 3, 4. And you're left with 1, 2, 3, 4.
Lost, yeah. Okay. Because the complex number, because the 2 reals must be equal.
Yes.
And the 2 complex must be equal. One is the opposite of the other.
Yeah. Yes. That
What is
one
the
equals.
So basically,
Yeah. That one is the conjugate. Is
you
the
could-
complex
you lose-
conjugate of that one.
so
And these have to be
they're the
real.
They are the same, basically.
Yeah. 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 Yes. Exactly. Yes.
Especially, it's always hard, especially in your head.
Yeah. Yeah. It's pretty hard to do. Obviously, this would be easier if I had a blackboard. Yeah. Yeah. So that's why. So that's why you have, and that lines up, right? Because an electron only has 3 degrees of, there's 3. Right. So it works out, works out. Now, why electron spin is a 2-level system? Well, that's there we have to go back to the that there are fermions is a thing which transforms correctly under the Lorentz transform. We're going to do this in a sec, right? We're going to do the Bloch sphere.
Oh, that one.
Yeah, I'm not going to talk about from a particle physics perspective, but obviously 2-level systems are all isomorphic, right? So
Sorry, 2-level systems, huh?
2-level systems are all obviously isomorphic, right? So I'm going to talk about qubits.
What are those isomorphic? Isomorphic means that they don't
vector
they don't
spaces.
change shape. I don't remember what isomorphic means.
Isomorphic means that 2 spaces have the same structure.
They can be mapped on each other
Yeah, that they're
with an isomorphism.
so.
Okay. Sorry,
So,
because it's
so all
these-
3-dimensional
so
vector spaces
language-
are equivalent.
Oh, sorry, all 3?
All 3-dimensional vector spaces are equivalent.
Yes,
All
correct.
2-dimensional
Are
vector spaces are
isomorphic.
equivalent.
Okay.
Not the case that all infinite-dimensional vector spaces are equivalent.
Let's not complexify too much.
Yeah, but yeah, all finite-dimensional Hilbert spaces,
Sorry,
the ones you learn in high school are the only
No,
essentially the
we
only
don't do
vector
that in
spaces.
high- We don't do Hilbert spaces in high school, sorry.
No.
Not,
Yeah,
I
no.
don't know in France, but in Italy we don't do that.
Fairly hard engineering.
Yes, sir.
Sorry,
I
did I say Hilbert when I meant to say vector? I mean, but
vector
yeah.
spaces we do it in high school, yes.
Yeah.
But no Hilbert spaces.
That's just the generalization to infinite
Yeah,
dimensions.
but from result. I think that the worst is the way we are taught the complex numbers. Because if you understand complex number easily, everything is much easier.
Yeah.
But I think that the way it was taught to us, I don't know if it's the same in France, the fact that already the fact that it's called complex.
Yeah, they scare everybody off with having this stupid name imaginary. It's like, it's so stupid. All numbers are imaginary, or to believe Kronecker, like God created them. They're not real. You can never measure pi You can never have pi of anything. It's not real. It's an abstraction. Like all numbers are abstractions.
I think the complex
Well,
number is-
Kronecker says the natural numbers were created by God and all else is a work of man. That's probably about right. Of those stupid meaningless things that famous quotations. That's one I like the most, right? It's like at least it admits that the real numbers and the rational numbers and the complex numbers are all equally abstractions that don't exist in physics, right? No, you can't measure 1/3 of something. How can you possibly have 1/3 of something?
1/3 you can.
Exactly 1.333333333.
No, 1/2, yes you can though.
1/2 maybe.
You can split in half something, come on.
Exactly in half? You can split something exactly in half? So it has like...
But so you can't multiply by 2 something.
If you have 2 buttons and half is 1 button.
Yeah, okay.
It's the same with multiplying.
All right,
It's the same
right,
with
fine. Okay,
multiplying.
maybe I can accept the
How can you
rational number.
multiply a length? Exactly. It's the same issue.
All right. Yeah, good. No problem. All right. So finally, guys, we're going to do some quantum computing. I know it took us a while to get there, but... So an electron spin, which we're talking about, is just one example of a 2-level system. 2-level system is something which has 2 states, is the basis. And now we're going to abstract over all such systems, and we're going to write 0 and 1 instead of up and down. And we now have permission to call this a qubit. All right? So in information processing, in quantum information, we talk about 2-level systems as being qubits. And of course there are, in terms of like actual physical actually existing quantum computers, there are a great variety of ways in which a qubit is realized. The most common one, today is a superconducting qubit where you have some superconducting circuit and it represents states of currents flowing around, this way or this way, right? And so it's something actually quite abstract. But there are other kind of qubits. There are, there's photonic quantum computing. There's, topological qubits, which Microsoft claimed to have actually existing, and not everybody believes them. And there's there's cold atoms, and there's lots of different things. But the point of them all is that they're 2-level systems. And we're going to write these things we're calling left and right as plus and minus. Okay, why plus and minus? Well, because one was 0 plus that over square root 2, and the other one was 0 minus 1 over square root 2. Okay. So, this bit's good, guys. People like this bit. This starts to give you a bit more of a geometric intuition. So, the state of a qubit is given by 2 complex numbers, right? The coefficients of the 0 and 1 basis states in the state of the qubit. And because they're 2 complex numbers, they package 4 real numbers. The real and imaginary parts. But we also have a constraint. A constraint on a quantum state is that its magnitude, its length has to be 1. So we lose 1 degree of freedom. So and this is necessary, so the probability sum to 1. Okay, so we have one equation here, which is constraining 4 degrees of freedom. So we're left with 3 degrees of freedom. Now, let's do an experiment. Let's try multiplying our state psi by a phase, e to the I theta, so that's a complex number with magnitude 1. We can write all such complex numbers in that form. And then we'll put it in a sandwich. Sorry, we'll take an arbitrary observable A and put it in a sandwich with this state. So I get, I lost my pointer because of the battery running out. But so if we dagger this and turn it into a bra, then the complex number e to the I theta gets complex conjugated, which is the same as taking minus theta, taking the negative of its phase, of its argument. And so that's the bra of our state after this transformation. Well, after multiplying it by this complex number. We take these. Now, matrices go through numbers. So these two numbers just meet up there, and we know how to, the index laws from year 8 or whatever in high school tell you what to do with minus e to the I theta times e to the I theta. They just cancel out. And so we get the same expectation back again. And this is a general property of all quantum states, is that multiplying them by a phase does not change any observable value. Okay? So there was a redundancy in our representation of quantum states. They have a phase which is not physical. Okay? And so that way we lose another degree of freedom. Every quantum state has an ambiguity in its overall phase. So finally, our qubit state has only 2 degrees of freedom, which is to say the state lives on a 2-dimensional manifold. Okay? Geometrically. But what's the, topologically, excuse me. But what's the geometry of this manifold? So we have two coordinates, right? So it's some manifold, right? But what's the geometry of that manifold? Well, to find that out, figure that out, we can do a trick that's very common. We can write the state in this form. We can introduce an angle. If we have two numbers which we know their squares sum to 1, which is this case because of the restrictions on probability summing to 1, then we could just use, by the magic of year 9 trigonometry, right, from high school. We know about triangles, right? We can write that as, we know the formula that cos squared theta plus sine squared theta equals 1. Okay? That's a standard formula you've all heard before in your lives, okay? So cos theta and sine theta are 2 numbers which satisfy this property that we required in order to get the probabilities coming out to 1. But that's not quite right for complex numbers. So for complex numbers, we get an extra, we have the possibility that there's a phase between the two things, okay? So we need to add a little phase in there. All right, anyway, the point is, I don't have a blackboard, so I can't do any better than just waving my hands a bit. The point is that you can write any qubit state in this form in terms of an angle theta, which represents how much of the probability, or how much of the amplitude is on this state, and how much of the amplitude is on the other state, and then a phase between the 2 qubits, okay? Then there's another phase, which is the global phase, but we don't care about the global phase, right? That's irrelevant, that's unphysical, it doesn't affect any observables. So we can put any quantum state in that form. Note, two real numbers here, theta and phi. And we can interpret them as spherical polar coordinates. And so that way we get this guy called the Bloch sphere. It's a representation of the state of a qubit of a 2-level system in quantum mechanics, of a qubit in quantum computing. And it has an interesting geometry. So okay, it's a ball or a sphere or whatever. The 0 state is at the North Pole. The 1 state is at the South Pole. The plus state is coming out of the page here, and the minus state is going into the page, and then there's another 2 states which are the eigenstates of the y observable. Now notice something funny about here. Tell me where in ordinary 3-dimensional geometry, ordinary Euclidean geometry, excuse me, a vector that's perpendicular to 0 would be. Would be on the equator, right? On the yeah. It has to be, it'd be one like this one or this one coming, like they're like this, right? Okay. Here is 0 and 1 are the basis vectors. They're orthogonal, and here they're like this. Okay. So even though we draw this as a sphere, it is not a sphere with Euclidean geometry, or embedded in Euclidean geometry. Okay, so it's a funny geometry. The orthogonal states are the North and South Pole. And the plus and the minus states we already know are not perpendicular to neither of them. Plus and plus has an overlap with 0 and an overlap with... this has the incredibly weird result that if you take this state and you rotate it all the way around and all the way back up again, you don't go back to the same state you started out with. You have to go around twice. I'm sorry? The mathematicians and physicists use different, have a different convention. So maybe that theta is. I always get a little confused because there's two different ways you can do this. Let me see. Theta on 2. Okay. No, that's. This is good. I'm good. Yeah, sure. Sure. It can go. You can keep going around. Yeah, sure. No. I think it's So this is theta. So theta equals pi on 2 would take you to the equator, and theta equals pi would take you to the orthogonal state. That's weird, right? Because normally theta equals pi on 2 would take you to the orthogonal state, right? Here theta equals pi gets you there. Theta equals 2 pi gets you back to the North Pole, but you don't get back to the same state. And so you have this, this kind of very weird behavior where if you take an electron and you walk around it twice, you walk around it once, you don't get the same, like it's not self-similar, right? It's not that's the right word. You have to walk around it twice to get back to the same state. Now, you need to be a little bit careful making that statement because, as I've said, global phases aren't observable, and this difference is a difference in phase. But it does become observable once you start looking at composite systems. Okay, so there are some weird things here where related to that fact that to get back to the same state you have to go twice around the Bloch sphere. Okay. Move on to a quantum circuit. What's a quantum circuit? So in order to understand, and be able to think about algorithms and stuff, so people, latched onto, idea in classical computing, we have this notion of circuits with gates. So we have gates like the NOT gate, the AND gate, and you draw lines between them representing information flowing through the circuit and producing some result of the computation. Okay, so when people started looking at the idea of quantum computing and quantum information processing, they wanted to have a similar kind of representation of that. Okay, so they came up with the idea of let's break things down into gates, which is some tiny operation operating on 1 qubit or 2 qubits or whatever, and a circuit, which is a flow. A flow of information. Now, a circuit is a terrible word because it implies that there's something cyclic, or in fact, there's no actual circuit in a quantum circuit. It's purely one directional. Now, I keep coming back to this, important thing. You've heard this 1,000 times. So probabilities must sum to 1. So any process, any quantum computation, must preserve the length of a vector. The length of this quantum state of the whole system, of the whole quantum computer or whatever, of all these qubits tensored together, has to stay 1. Okay, we can't lose probability. The system, the probability of it, you have to have, if this qubit was in state 0 with probability 1, we can't say, oh, it's in state 0 with probability 1/2 and state 1 with probability 1/4. No, probabilities have to be conserved. So there are only certain kinds of matrices which could represent such a process, right? It has to be a matrix which preserves the lengths of vectors, and the matrices which do that in a complex vector space are called unitary matrices, and they satisfy this property, which is that U dagger U equals the identity. Okay, so unitary matrices can represent things which can legit represent a process. This is why you will hear people talk about quantum mechanics exhibits unitary time evolution. Okay, that the evolution of a quantum system conserves probabilities and can be represented by a unitary matrix. This means that, by the way, it's easy to show that this means that the inverse of the matrix is just its adjoint. Every eigenvalue of a unitary matrix has magnitude 1. Okay, it can be a complex number, but its magnitude is always 1. And they are the analog of rotations in complex vector spaces. So I'm sure you've seen rotation matrices in real vector spaces, but these are the analog in a complex vector space. All right. Now, last time we were talking about spin observables, Sx and Sz. They had the annoying property of having this half out the front of them. And now we're just going to drop the half. And we're going to talk about the matrices X and Z, which are the same matrices, but without the annoying factor of half. And these guys are your friends, right? These are the matrices, the most popular matrices, okay? X, Y, and Z, or in physics, they're usually, particle physics, they would be called sigma X, sigma Y, and sigma Z, or sigma 1, 2, 3. In quantum information, they're called X, Y, and Z. This is the one we've seen before that we started out calling flip. This is a new one we haven't really seen before. Actually, we did. We saw I times, or negative I times that when we calculated the commutator of these guys. That's no mistake. That's no coincidence, as you can imagine. And this is the Z-spin matrix, which we saw before, all multiplied by 2. Okay, so we've seen all these guys before. Is Y Hermitian? So dagger means two things. Transpose it and complex conjugate it. Which one do we want to do first? Let's transpose it first. We swap those, we get minus I there and I there. Now we complex conjugate it, we get minus I back. And so it's Hermitian. And we already know the other two are Hermitian. So these are called the Pauli matrices, and together with the identity matrix, they're a basis for the space of 2 by 2 Hermitian matrices, all right? Which is what we were talking about in the break, right? You know, the reason, you know, so the question was, well, why the hell did you pick that matrix, right? I only have, you know, if I start out, you know, when we're representing spin, if I start out representing the spin in the z direction with that one, then I want x and y to be perpendicular matrices, right, in the space of matrices, and I only have two options then. I'm only left with two options, y or x, right? So we arbitrarily name x x and y y, but essentially this space of 2 by 2 Hermitian matrices has 4 basis vectors, one of which is the identity matrix, one of which is z, one of which is x, and one of which is y. Okay, and they're orthogonal in the sense of they're orthogonal in the space of matrices. It's what did I say? It's a space of 2 by 2 Hermitian matrices is a 4-dimensional vector space. Yeah? I want to say no, but maybe you have a good reason for thinking. To go out and ask me again later. I don't want to like start thinking out loud here. Right. So anyway, the point is, in this space of 2 by 2 Hermitian matrices, those are the only ones which are orthogonal to each other, and that's why spin we have 3 possible directions of spin, dimensions of spin. We use those as observable. Are these matrices unitary? Yeah, they are. You can check that for yourself, but they are. It's obvious that this one is. Just check it out for yourself. It's good to verify things like that, but they are. So in the block sphere, how do we interpret these guys? X is a rotation of pi around the x-axis. So if I start with a something in that state, around the x-axis, you know, it's going to be a rotation of pi like that, right? Which we knew, right? We knew that x exchanges up for down, okay? I don't have a blackboard here, so you're just going to have to look at my terrible. This is x, this is up. So we knew that x did that, okay? So it's a rotation around the x-axis. Y is a rotation of pi radians around the y-axis, and z is a rotation of pi radians around the z-axis. That's why they're called like that. And, you know, it's good exercise to, you know, compute some of these. It's super easy. Just matrix, 2x2 matrix multiplication, but it's cool. Now we're going to meet another matrix. Sorry, I have a totally different slide on my screen here. Oh, that time it worked. That was weird. So this matrix H, I can't motivate where this came from. It's just some matrix I put up there. Let's find out what its action on the state 0. This state is. Oh, I don't have a blackboard. Wait, do I have a slide which does it? Oh, damn it. Okay. So if we have 1, 0 here, we're going to get 1 there. We're going to get 1 there. 1. Okay, so the action of this on 0 is going to be plus, the plus vector. Sorry, I should have done this on the slides. And its action on the 1, on that state, is going to be the minus vector, which I think points this way. So it exchanges up and down for left and right, essentially. Okay? 0 and 1 for plus and minus. Okay? Or put in another way, expressed in another way, it takes what we use it for all the time in quantum computing, is it takes the 0 vector and puts it in the superposition of 1 and 0. Okay? So it's like, it's the equivalent of a coin toss. What's the closest equivalent of a coin toss? And it's also a rotation in the Bloch sphere. So in fact, every single qubit gate is some sort of rotation around some axis in the Bloch sphere. And why is that? Because we have this two-dimensional manifold, right? The state has to stay on this manifold or else we've lost probability. So anything has got to be just some kind of rotation from some, you know, state to some other state. A quantum circuit is a series of gates acting on one or more qubits. So for example, this is the first example. If we take the Hadamard gate, we apply it to the 0 state, then we get out the plus state. That's how, and that's all that circuit diagram says. And as I said, it creates the equal superposition of 0 and 1. And it looks a bit like our coin toss operation, but here's where it's going to be different. What happens if we repeat? We know what happens if I toss a coin twice? It's equivalent to tossing it once, right? Yeah. It's idempotent. Is that the right word? I always get confused between evolution and idempotent. But idempotent, I think, is the right word. But what about with H? Well, let's see with matrices. Okay, we're going to compute T squared, which is the application, which is the result of, which is the process which tosses a coin twice, and H squared, which is the process which applies the H gate twice. And you can see that when we square T, we get T back again. As I said, it's idempotent. I think that's the right word. And with the Hadamard gate, we square it. We don't get the Hadamard gate back, we get the identity back. I think it's called an involution. So if I apply the H gate twice, that's as if I did nothing. So even though this is a lot similar to tossing a coin in the sense that it takes this state and then puts it in a superposition, an equal superposition of 0 and 1, if I apply it twice, if I do it again, I get back to my original state. So that's very different. Exactly. That's on the, hold on, right? So the Hadamard gate is reversible, right? It doesn't destroy information. It doesn't create entropy. And in fact, this is a universal property of unitary evolution. Oh, what happened again? Is that unitary evolution is deterministic and reversible. Pure quantum states are zero entropy states. That's very different to a classical, yes. Yeah, okay. A pi rotation will take us to the same position on the block sphere, but with a different phase. H squared, okay. No, I mean we just showed that h squared is exactly the identity, okay? So it has no, so h squared recovers the state exactly, okay? So it's as if you did a 2 pi rotation, except it's not actually about that axis. Yeah, well, but it's not. It's a rotation around a different axis. It's a rotation around some funny axis here. I don't want to say how many. You can exponentiate these guys, and then you can get. Don't think of it like that. Think of it as a it's a good question. Isn't it? Yeah, but I mean, she has a point, right? She's like, why is it? Because I said it's a rotation of pi on 2 and followed by a rotation of pi. And she's like, but to recover the original state, we should need a pi rotation of 4 pi, right? And yeah, maybe because we're not in the. Yeah, because we're not in the infinitesimal representation exponentiating. It's probably something like that, right? We're not in the Lie group. We're not in the. Yeah. Yeah, I think he's right. I think what he's saying is right, and I think the reason is that to be able to turn these into actual rotations with angles in them, you have to look at the Lie group, the Lie algebra, not the Lie group, and you have to look at their infinitesimal form, and then you exponentiate them, right, with a theta in them. And then you can look at how they incrementally rotate round. But we are looking at but we are just taking them and applying them, so that kind of way of thinking about incrementally applying them doesn't quite work, right? And so he's saying that h, obviously just reverses itself because h squared is 1. So I think that's not a good answer. Let me think about it later. I don't want to, get tied up on this, but I don't think it's. I think you have to go to a different representation to be able to think about these things in terms of incremental rotations, right? Anyway, let's just leave it there, because otherwise I'm just going to make more of a fool of myself. The important thing is that if you apply it twice, it just undoes its own effect. What he's saying, it just inverts it, right? It's its own inverse, I think. Is the way to say it. Well, obviously it is. So how can we actually get entropy in a quantum system? Well, we have to measure. So if you think about it, right? I've taken this state, I've applied the Hadamard gate to it, and I've got a superposition of 0 and 1, equal superposition of this state and this state. Then when I measure it, if we go right back to the start when we talked about classical probability theory, I collapse the superposition and I get one measurement out. All right? And that is the operation which creates entropy. Measurement, in this way of thinking about it, trades a quantum superposition for a classical probability distribution. And a classical probability distribution can have entropy. Okay? So a classical probability distribution of probability a half up, probability a half down, has entropy. A pure quantum state, as produced by the Hadamard gate, does not have entropy. Another way of looking at this, and this comes back to what everybody's, questions about, this foundation, in terms of foundations or whatever, quantum mechanics. Another way of looking at this is simply that the measurement entangles the measuring device with the system. Or even better, if I'm there observing the result of this measurement, what's happening is that the state of my brain is becoming entangled with the system. Okay? So after the measurement, we have two states. We have an equal superposition of two states. One is the state the qubit is in state 0 and Gavin's head thinks it's in state 0. And the other is the state the qubit is in state 1 and Gavin thinks it's in state 1. Okay? So measurement is creating a correlation between the observer and the system. So that's a different way of, that's absolutely 100% mathematically equivalent and produces exactly the same consequences as thinking about measurement collapsing the superposition and producing a classical distribution of states. Now, unfortunately, in a real quantum computer, the environment is constantly measuring the system. Okay, it's constant. The system is in the quantum computer is in constant interaction with its environment. There's all kinds of little magnetic and charge perturbations going on, and so the system very quickly becomes entangled with its environment on over a space of microseconds or milliseconds, and that's what we call decoherence. Right? So we lose that quantum nature of the system and wind up with just a classical probability distribution from our point of view as an observer entangled, or the environment entangled with the system. And so once that happens, we can no longer do anything useful with quantum computing, because we could do everything with a classical computer, right? Once the system decoheres. So we have to protect that coherent state where it's not, where the system, where the qubits are not entangled with the environment or with the observer. So the way we talk about language, we talk about this is that this pure quantum state irreversibly decoheres, we're creating entropy, so it's irreversible, into a classical statistical mixture of quantum states. Okay, this state with probability this other state with other probability. Okay. Now, setting that issue of decoherence aside for now, there are lots of strategies being used to, all the time extend the lifetime of a coherent state of qubits, and the coherence time is increasing all the time. The best coherence times in labs. Let's think, let's suppose we can maintain a coherent state over time. So let's think about creating a state like this, which is a tensor product of a bunch of qubits in the superposition of 0 and 1. Essentially, this state is a superposition of all the numbers between 0 and 15. Okay, in this superposition, we have 0, 0, 0, 0, 0, we have 0, 0, 0, 0, 1, we have 0, 0, 0, 1, 0, we have 0, 0, 0, 1, 1, and so on, okay? Because each of these has an equal contribution of 1 and 0, okay? So this tensor product is a superposition of all these numbers. How could we create such a superposition? Just like that, trivial, just a bunch of single qubit states, single qubit gates, the Hadamard gate. And since quantum gates can be used to, obviously quantum computers can simulate classical computers because classical computers are quantum systems, right? So a quantum computer can be used to implement classical operations like an adder or whatever. And so this means that we can do, in principle, by creating a superposition of all these different numbers and then passing it through a system which simulates a classical adder, we can do, in principle, a computation on on all the numbers at the same time, right? But there's a massive catch. At the end of the computation, we have to perform a measurement. At that point, we collapse the superposition, and we get the result of one of these computations out. Okay? And so we've gained nothing. So if we're going to be able to have quantum computing provide anything useful over what you can do with classical computing, the quantum computer has to do something really, really clever while things are still in the superposition, before we measure, before we get a number out, to somehow take advantage of the fact that we're doing this, all these computations in parallel. That is not easy at all. Or maybe, let's say we have a crazy idea. We're going to create a superposition of all these numbers. We're going to do a computation on them. So now we have qubits, which is a superposition of all the answers. Let's make 1 million copies of this resulting state and measure each of them. And then we should have, in the results of those measurements, all the answers represented multiple times, right? And the question is, which I'm going to pose to you guys, is can this possibly work? Except that I'm over time at this point. All right. And the answer is, if we consider, I'm 1 minute over time, so I'm just going to skip over a bit and give you a quick rush through the answer to that question I just posed, right? In classical computing, something we absolutely take for granted, fundamentally take for granted, is that I can take a classical bit and make a copy of it. A perfect copy of it, right? Can I do the same with a qubit? What does that mean, taking a copy of something? It means, say, I have 2 qubits here. One is in state I, and one is in state 0. And it wants some operation, some quantum circuit, that's going to give me 2 copies of that state, I in both the qubits, right? what quantum operation could do that? Let's say we have a gate U which is able to do that. Then we don't know what UE is as a matrix, but we can write down what its effect on 2 qubits must be, on the basis, on basis vectors must be, which is enough. By linearity, we can obtain all the other properties of U if we know what its action on the basis is. So what we know about U is that it must take, is that applied to the tensor of 0, 0, it must produce 0, 0, and applied to the tensor of 1, 0, it must produce 1, 1. We know we can do this. We can do this in classical computing, okay? So this bit's easy. This much is easy. Additionally to that, we must be able to take the superposition of 0 and 1, the plus, and produce plus plus. And now we want to compute. So let's go ahead and compute what U applied to plus tensor 0 is, making use of these things, these properties we just written up above, okay? So we're saying we know we have these properties, and now let's compute, and now assuming we have those properties, let's compute the action of U on plus tensors with 0. Okay. You can check the result of that on the in the textbook. The answer is that there is no such unitary gate. Okay, it's very easy to show that no such gate exists by just following through that computation I was proposing there. You arrive quickly at a contradiction. And so it's impossible to copy a state of perfectly copy a state of a qubit. And so that means that that approach I hypothesized there can't possibly work. Right? And so you really, really need to do very clever things in order to be able to get anything useful out of quantum computing. And that's why, still I would say that it's very hard to, I would say, it's very hard to see any, see what the applications of quantum computing are going to be. So it needs to be a lot of, really smart thought put into coming up with algorithms for quantum computers, just because it's so difficult to get them to do something that classical computers can't do. We know that they can do some things that classical computers can't do, but we need them to be able to do useful things. Okay, thank you very much for staying all the way to the end of this 3 hours. I'm sorry I ran out of time a bit at the end there, but hopefully you guys got something out of it. Now, to pick up from there, and this is the book that everybody uses by Nielsen and Chuang. The no cloning theorem is on page 24. So that's really a short way into the book. So and that tells you how easy it is to actually do the no cloning theorem. And even better, this series of videos by John Watrous on the Qiskit site is like a really good. It's just really, really good and very clear. So you can pick up with that. Okay, as I said, thank you very much.